Hello? Okay, welcome to this morning session. Hopefully the dinner was really nice for everyone. It was for me. So the first speaker of this morning is Holger Rauhut from LMU Munich, and I'm glad that I was just pointed to a Viennese connection that he has, which is that he did a postdoc there. Is that correct? Yes. Okay.
Okay, yeah. Thanks. Thanks especially to Helmut and Lagrange Center for making this workshop possible, bringing us to the very nice city of Paris, while establishing a Paris-Vienna connection, maybe. Okay, so yeah, this is about implicit bias in deep learning. I guess yesterday we already heard something about that. This double descent curve is also connected to this, although this is taking a slightly different twist. Yeah, so I will first introduce what is meant by implicit bias. So this is well, in the setting of over-parameterization in deep learning. So when you have more parameters than training samples, and then the learning algorithm gets a great influence of what is computed in the end. I guess the theory is still in a somewhat early stage. So in order to prove theorems, one has to simplify a lot. And so I will proceed by increasing complexity. So start with linear diagonal networks, then fully connected linear networks, and then some preliminary results about two-layer ReLU networks. So here I basically will present results of others, in particular Etienne Boursier and Nicolas Flammarion. We are also working on this, extending this work, but it's, well, almost finished, but not yet out. So I will just point to what we have been doing, but I think it's an interesting direction. Okay, so let me start with this well, graph showing the size of the models that are currently used. And so you see on the x-axis the publication date going until 2022. So this is from a paper which appeared in that year. Maybe there is a more current overview on this, but I haven't found one. So this is a log scale, and so this is going up to, well, this is 10 to the 13 parameters. So the models are really getting very large. Well, for instance, there is an estimated, well, OpenAI didn't really release what the numbers of ChatGPT-4 are, but there are some estimates which, well, according to which this is 1.7 trillion parameters, so a lot of parameters, and in particular, often we have more parameters than the number of training data. And so let me report on, well, this is already quite some years ago, and maybe there are more current numbers on this, but the phenomenon stays the same. So this is coming from the PhD thesis of Zhang in 2017, or, well, from this paper, 2016. So here they tested various convolutional networks on the CIFAR 10 datasets. with about 50,000 training samples, and trained these different architectures via stochastic gradient descent. And so it's not so important what these are exactly. What is important is the number of parameters. And in particular, here is the oversampling ratio, or the amount of overparametrization. So the number of parameters divided by the training number of training samples. So this is a quite large factor. And what they observed is that they always could achieve training loss 0. So they basically were able to fit the networks exactly to the data. So training loss 0, and then there is no question that we actually achieve the global minimizer, because we cannot get below 0 with the training loss. But what is important, of course, is how these models behave on new data. So we are interested in the test accuracy. So that's what we want to achieve in the end. So the point is not to interpolate the data exactly, but actually to see whether on future data we get good predictions. And so here is the test accuracy, and so Cypher 10, that's 10 classes. So if we do a random guess, it's 10%. So these models behave much better than random guessing, and in particular the last one is quite accurate, and I guess nowadays the numbers are even higher. So if you think about this, this is a bit puzzling, because classical statistics would tell you that you're overfitting at some point, just fitting the noise, but it seems that even like the generalization error even decreases with increasing number of parameters. Okay, so we have already seen this in this double descent curve. So beyond the interpolation, well, the point where you have exactly the number of parameters equal the number of samples, then afterwards you get a decrease. But here we even achieve a 0 training loss. So here's a picture. So if you have underparameterization, and here you have your data, and your network does something like that. But if you have overparameterization, you get many networks interpolating the data exactly. But in between the data, basically the networks can do what they want in some sense. So you could also imagine that you add like virtual data points that you place somewhere here, and then you always find networks that also interpolate those data points. So you can do crazy things, or you can have networks that behave quite tamely. And so the question is why we find something that interpolates well, or that generalizes well, because that's not built into the learning framework. We just have the loss function, which we minimize, and we achieve a global minimizer, but there are many global minimizers, so the question is actually which one do we get? And in this scenario, the optimization algorithm that we use has a huge influence on what we compute in the end. And this is meant by implicit bias. So the algorithm has an implicit bias on what we compute. And this is not meant in the negative sense. So in the social sciences, I guess implicit bias is something bad, but here is something good if the implicit bias leads to good generalization. So and with the optimization algorithm, we also mean like the choice of initialization, for instance, or like hyperparameters such as learning rates, or anything that influences the algorithm. Okay, so the question is, can we understand this? And well, in particular, understanding the generalization error in deep learning requires also that we understand the optimization algorithm. So classically, in classical learning theory, you usually separate the analysis of the algorithm from the analysis of the statistical error. But here, this is, if you want to understand this is no longer possible. So the working hypothesis that we have is that the implicit bias of these well, variations of gradient descent, stochastic gradient descent, I mean, there's also Adam and all these algorithms around, they lead towards solutions of low complexity. So the idea is that in the end, if we want to have good generalization, we cannot have like something which is really complex. So in the sense of Occam's razor, so often nature prefers simple solution, but of course describing what exactly is meant by low complexity, that's a bit the challenge here. And also why then algorithms lead to such solutions, that's also part of this. So in order to have a chance, so as a mathematician, you always, well, probably it's a bad idea to start with networks with 27 layers and 10 to the 12 parameters. So you try to reduce to something simple, but which still captures the essence of the problem. So we want to study problems, maybe first of all toy problems, where we have many global minimizers, so that was one important feature. And that there should be something like a factorization or compositional structure as in neural networks, because this seems to, well, be tied also to the structure of neural networks. And then one can look at algorithms. So in terms of simplicity, it's useful to start with gradient flow. So that's an abstraction of gradient descent or stochastic gradient descent. And then you avoid taking into account step sizes, although one has to be careful that may have also a significant influence on what one gets in the end. And then once we understand gradient flow, we want to go to gradient descent, maybe stochastic gradient descent or like Adam and so on. So what's the general idea? At least this is a hope or wish that if you look at the limit of gradient flow or gradient descent, that this limit satisfies another optimization principle where the limit, well, interpolates the data, but then minimizes another function, a regularizer, that sort of promotes low complexity, sparsity, low rank, or something like that. And that regularizer may depend on the algorithm, but also on the network architecture. So it will make a difference whether you consider fully connected or convolutional or transformers or whatever. And also maybe initialization will play a role and possibly step sizes. So, and the hypothesis is that for suitable initialization and step sizes, that this promotes somewhat solutions of low complexity. So with low complexity, I mean something like sparsity, low rank. It may also be like low tensor rank, but could also be some structures that we don't really understand yet. There could be connections between all the weights in the network. So I think this is still a matter of finding out. And then the connection to generalization is the idea that real-world data distributions are not arbitrary, but they can be modeled well with networks of such low complexity structures. So, well, following Occam's razor principle that we should prefer simple solutions. Of course, that's a wish, and it's not clear whether something like that can always be shown, but I will give you one example where this is true. So we start with a model problem, which is quite simple, so it's connected to sparse recovery. So yeah, at some point, well, I guess you know that I was dealing a lot with sparse recovery, and so at some point I thought I'd do something different, and then it led me back to to this thing. So we look at the matrix with fewer rows than columns, and look at this problem. And if you look at the minimizers, I mean, there are infinitely many. So usually all solutions of that equation, if there are no solutions, then, well, you can still, it's connected to the pseudo-inverse, and then you still have infinitely many global minimizers. And then we also need to take in, well, as I said, we want infinitely many global minimizers, but also like a factorization structure. And so what we do, we take X and simply write it as a Hadamard product of several vectors. Okay, so you can, this Hadamard product is the component-wise product, and of course you can, if you write X as the diagonal of a matrix and the W's also as diagonals of a matrix, then this is simply the matrix multiplication of the diagonal matrix. That's why this is, you could call this linear diagonal networks. Okay, and then you form a new functional by plugging in that factorization into the original, and then the task is to minimize this functional via gradient descent or gradient flow, and ask what are properties of the minimizers. Okay, so to avoid misunderstanding, I'm not really looking for new algorithms to solve this problem, but it's just a means to maybe get ideas what happens in general if we consider such over-parameterized problems. And it turns out that this is connected to the compressor sensing task to compute sparse solutions of AX equals Y. And so the standard, or one standard approach is L1 minimization, where we minimize the L1 norm subject to this equality constraint. And okay, so, and for technical reasons, we are not only using this approach, but also one where we take actually two factorization and plug in the difference of the two factorizations into the functional. So this is because in the setup we are considering this here, the gradient flow can only lead to solutions with positive entries, and if you want negative entries, we have to go to this variation. Yeah, sure. I mean, we will, well, in our analysis we go to a simplification, but still in the end, you're not so much interested in the individual factors, but in the end in the X that you get. So yeah, so I mean, okay, of course, you can apply the algorithm and then form the product again and look at the flow for X. And for each n, you get a different flow. So it's not like, I mean, otherwise this wouldn't be interesting. But it's really that you get something different. I mean, at first, this looks a bit stupid. You have a nice convex problem, and then you make it non-convex, but okay. Okay, so if you do not factorize, then this has a, if you initialize at 0, this actually converges to the least squares solutions, so this is very well understood. But here you actually see what the implicit bias is in some sense. It's minimizing the L2 norm. And now, yeah, so in the general case, we look at the gradient flow for each of the factors. So the blue one is the version where we have just one factor, and the red one is the one where we have the difference of two factorizations. And so we take the gradient with respect to the case vector here and look at the evolution according to this differential equation. And we initialize somewhere here with W0 or U0 and V0. And then we can look at the product again, and that's actually the interesting quantity, the x tilde, or the x hat, which is the version where we have the difference of two factorization, and we ask about properties of the limit. And so we simplify further by looking at the case that we initialize identically, and then it turns out that for all t, the vectors stay the same vectors, and then we can write this simply the x tilde as this one vector to, like, okay, this means yeah, so we multiply, well, we exponentiate each entry to the n, and it turns out that these vectors are the gradient flow for this functional, where we simply exponentiate each entry in the vector w. Or here's the version, we have the difference of two vectors. Of course, this is a bit of a simplification, but as a first step, it's very useful. And then we even simplify further and initialize all entries of these vectors the same. So it's alpha times the vector of 1, so all the coordinates are alpha. And it turns out that the scale of alpha is very important, so you have to think of small alpha. Okay, so here are some numerical experiments comparing this with the standard approach L1 minimization for sparse recovery. So we take as matrix A a Gaussian random matrix, and so I think it's dimension 20, and here is the number of measurements. So n is 20 and m is here on this axis, and then we vary the sparsity. So we generate the right-hand side y as ax for some sparse vector, and then try to recover that vector. And here white means that we always are successful in recovering, and black means that we are never successful. So that's basically the benchmark. Now, if we do not factorize and run gradient descent, then we basically get this picture, so we don't really get sparse vectors back. And this up here we have, well, the number of measurements equals the dimension, so okay, in this case we can recover. And now here is the situation for 2 factors, and here for 3 factors. And so you see that we do promote sparsity by this approach, which at first is a bit surprising because this is not really built in, or at least not apparently. Well, once you analyze, maybe you understand that's somehow built in, but yeah. And even like increasing the number of factors, well, has an influence on how much we promote sparsity. So with more well, deeper networks, this promotes even more sparsity. And here's the version where we also allow negative. So this was the variant where we only look for, well, we start with positive vectors with positive entries and only recover positive entries. And here we can also get negative entries. But it's basically the same observation. Here we even went to n equals 4. Okay, so so here's a theorem about this. So we assume we have at least 2 factors, and assume that the set here of positive solutions or non-negative solution is not empty. And then the first statement is that actually the limit exists and also is in the set. So the limit actually satisfies the equation exactly and gives you positive or non-negative entries. So we do interpolate. And now the question is, what is the property, or which type of vector do we get? And so here we compare with L1 minimization. So Q is the norm, the L1 norm of the L1 minimizer. So it's the minimal L1 norm in S plus. And these are beta 1 and beta mean are parameters of the initialization. And so if beta 1 is small enough, then the difference of the L1 norm of the limit and the L1 minimizer is less than epsilon times this Q. And epsilon is this quantity which depends on basically, the best way to see it, this formula is, so it depends basically on the ratio between beta 1 and Q. So beta 1 is the scale of the initialization. And so if beta 1 compared to Q is small enough, then this epsilon is small. So for small initialization, we get close to the L1 minimizer. Yeah? Yes. So we also have a result for arbitrary initialization, and but then we have to look at actually weighted L1 minimization, where the weight actually depends on the initialization. So okay, I mean it's more technical, but I mean we have the result, but this is the nicest one to present. Okay. So basically if we initialize small, we get something back sparse or almost sparse. So a little bit concerning the analysis. So there were these people, Gunaseka, Lee, Sudri, Srebo, provided a general framework for analyzing these things. So they were looking at evolutions of this type. So think of x of t as the product of these w's, and then you can actually write this. So here's the standard gradient, and then due to the factorization, you get like this multiplied the standard gradient by some function. And if that function, so that's a matrix, if that's actually the Hessian of some scalar valued function, and then they provide an analysis. So you introduce the Bragman divergence with respect to that particular f, and so they have this result if the limit exists and the loss at the limit is 0, then the limit satisfies this optimization principle. So here you have the Bragman divergence of x, and the second argument is the initialization. So this shows how the initialization actually comes into play here. And they look at these particular types of losses. So so you satisfy, well, you minimize that term subject to this equation. So this is actually what also happens in our case. So our result holds more generally. So also for large initialization, but then the Bregman divergence rather behaves like an L2 minimization. So so in the end you need to relate here the minimizer of this functional to the minimizer of the L1 minimization. So that's in the end what we do, and we prove that these statements hold true for our situation. And the Bregman divergence that turns out in our case are these ones. So for n equals 2, we basically get the Kullback-Leibler, well, we do get the Kullback-Leibler divergence. But for n larger than 2, we get these different expressions, which have also appeared in statistics before. I forgot the precise name, but yeah. So that was basically what one needs to work out how this f looks like, or one has to have a conjecture about the f. And then we can also analyze the general case where we get also negative entries, but the result is basically the same. So the expression for epsilon is exactly the same, taking into account the sum of the two norms of the two initializations. Okay, so here one analyzes the difference of the L1 norms. Well, if you are actually interested in the L1 norm of the difference, you can also do this. If A satisfies nice properties, namely the null space property, then you can, well, relate the difference of the L1 norms to the L1 norm of the difference. And so in some sense you can view this now as an algorithm for compressive sensing and get error guarantees. So if you get this number of measurements, like that uses that the Gaussian random matrix satisfies this null space property, it's high probability you get an error bound like this. Maybe a few comments on this. So these results actually require small initialization scale. So you might ask why not initialize at 0. The problem is that 0 is a critical point of the function that comes from the factorization. So you cannot really start with 0. And if you initialize very small, then the gradient flow needs a long time to escape from 0. So in terms of numerics, it's actually, you have this defeating, on the one hand you want a small alpha, but for numerics you want a larger alpha. So the question is whether you can actually get that also with larger alpha. And you can do some tricks. And so here we analyzed what is called weight normalization. So you actually further split the vector into the norm R and then the direction, and plug in both parameters here separately and run a gradient flow with respect to both of them. And the trick is to have different learning rates for both of them, and in this way you can actually work with larger initialization. And so basically you can have the same effect as before, but so here you get the parameter that you had before multiplied by some number which effectively lowers the initialization quite a bit. So, but let me, let me continue here. So one question is whether, okay, so these were results for gradient flow, and of course in the end we use gradient descent, and also the step size should play a role here. So there has been an analysis of stochastic gradient descent in this paper for n equals 2. They also analyzed gradient descent. But it also, this analysis somehow works just for n equals 2, and currently a PhD student of my group is well, trying to extend that. I mean, the results are there, almost there, for n, well, actually n larger or equal to 3. So here one has to do it slightly different. So in the end, we view the iterations as a perturbation of mirror gradient descent, and it turns out that I mean, somehow this becomes much more technical than the gradient flow case, because you have all these error terms that you have to carry along, but this is also possible. Yeah, so then the next step is to go to fully connected neural networks. So the diagonal case is, of course, a quite drastic simplification. And so you may look at the problem of recovering a matrix with low rank. And here one can do the same. Basically factorize this W into well, a product of matrices, now a standard matrix product, and plug it into this functional and apply gradient descent or gradient flow. Of course, if we have restrictions on the dimensions of the individual matrices, then we build in a rank constraint, but we don't want to do this here, so all the matrices are n by n. And so here the theory is, I mean, well, there's a little bit of theory, but to my opinion, it's not really satisfying yet. But one can do numerical experiments, of course. And so here we plot the number of measurements and the probability of recovery. And so we want to recover a 20 by 20 matrix of rank 2 using Gaussian random measurements. And so here are the different number of factors, so n equals 2, 3, and 4. And so for n equals 2, it sort of works, but for n equals 3 and 4, you basically get the same performance as for nuclear norm minimization, or even a bit better. But the available theory, unfortunately, makes very strong assumptions. The most convincing case, I mean, or analysis by Stöger and Sultan al-Kotabi, so they treat n equals 2, but actually look at a non-symmetric factorization, which means that, well, they actually factorize into W into U transpose, so take twice the same matrix, so it's a slightly different analysis. Okay, so here, I mean, one still needs to work a bit on this. So the last thing I want to talk about is extensions to a nonlinear case, so two-layer ReLU networks. So here, yeah, you all know the ReLU function, and so the neural networks that we are looking at are of this form. And the parameters are the WI, AI, so WI, AI, and given data, we look at yeah, the usual loss function. So for L, maybe think of the square loss again. And then we can actually look again at the gradient flow. Well, in this case, since the ReLU is not differentiable in 0, it's actually differential inclusion, but yeah. And yeah, now I wanted to show you some videos, what's happening. So what you will see in the videos is the evolution for each of the WIs in respect to time. So let me show this first video. So this is for one-dimensional output, 2 layers, 2-dimensional input, and so below you see the loss function, and so we initialize small, which means that it first takes a little bit until something happens. And here each dot represents basically the angle in like polar coordinates of one of the WIs. Okay, so let me show how this looks like. So you see that well, the neurons still stay small, but they sort of move. And now, I mean, many of them move in the same direction, but, well, increase value. And then there is another plateau, and then there is still another plateau. And yeah, now when the loss is getting close to 0, yeah, I mean, this one widens a bit up. So we haven't reached loss 0 yet, but what you can see is that, so what this means that if many neurons align in the same direction, this means that we again have some sparsity prior, because we could easily replace the sum, like these are like I think 100 neurons, so this is a sum over 100 terms, but if they all point in the same direction, or many of them, we could simply approximate this well by, let's say, a sum of 3 relos. So again, there is some sparsity appearing, and so let me show the next video. So this is basically the same, but going for a little bit longer. So the first part is now moving quicker, because we have, yeah, so that was the early phase. And then you see that a little bit more is happening. So the sparsity gets like, I mean, in the end you get something which is less and less sparse, but basically this adapts to the data. So depending on how the data looks like, you might get actually need more terms in the expansion. Okay, so this looks like this, and then so this was the scenario analyzed by Bossier and Flammarion, and what we are currently working on is trying to extend this to multi-dimensional output, which probably is also important if you have like several layers, because the intermediate ones will have vector values. So this is the upper one is the I mean the inner weights, and these are the outer weights, which are now also vectors, because we have 2-dimensional output. And so we see that we actually also get alignment for the outer layers. So this looks a bit like that. Okay, so yeah, some sparsity patterns arise also here. Okay, maybe I can stop here. Okay, let me go back to So if you look at this and look at the dynamics of the individual neurons, like the differential equation looks like this, where the D is this vector here, so that's basically the gradient, well, in general the subgradient, and we can look at the one with minimal norm. And now, what we see, I mean, we discussed balance stuff yesterday, so we also have that here. Now, the idea is if we have small initialization, the output of these neural networks basically is very close to zero for quite a long time. So the idea is to approximate the dynamics with one where this is basically zero. And then it turns out that the analysis is basically a gradient ascent with respect to this function on the sphere. So if you look at the directions of the vectors. And this is actually a function which is piecewise linear, where the pieces are determined by these signs, like basically on which side of the hyperplane generated by the data is. And then it turns out that the dynamics aligns with the critical points of G. So it's important to analyze this thing where D is actually coming from this, where we plug in here a zero. And so they have a theorem about that, so they can say what the length of the first initial phase is and what happens at the end of the phase, which is basically saying that at the end of the phase we are basically pointing in the same direction as the critical points of G. Or as like each neuron aligns with one of the critical points of G. And so as a consequence, so this means that usually many neurons align with the same critical points, especially if there are just a few critical points. So this shows sparsity arising in some sense. Of course, there's further developed after the first phase, and that's a bit harder to analyze, but the analysis also goes through it when you're in such a plateau, which seemed to empirically happen. And so what we're, as I said, we're working on, so we have a result on alignment for both the input weights and the output weights, and so we're submitting this to NeurOps. I guess some of you are aware that the deadlines are this week or next week, and then it's hopefully out. They are further contributors to this field, so they have also done a lot of work here. I didn't mention them all. And at the end, some general philosophical question. So as we've seen in the beginning, we usually start with networks having a lot of parameters, and now the rule of thumb is to use the number of parameters such that all this just fits into your GPU. But if we see that in the end we converge to something which has much lower complexity, the question is, do we really need to start with such huge number of parameters in the first place? I mean, people observe empirically that you get better performance if you increase the number of parameters, but maybe we just didn't find the right way to learn yet. Of course, it could be that the high dimensionality is required because of intrinsic hardness. Maybe it makes the optimization problem computationally easier if you increase the dimension, which seems a bit odd, but this could be a reason. Okay. Anyway, let me stop with this, and thanks for your attention.
Thank you very much, Holger, and good luck with the deadline. So we have some time for a quick question, maybe?
It's a good question. So currently we want to understand what happens in practice with the algorithms that are used. But of course, if you understand better what the implicit bias is, maybe you can turn this into an explicit bias. But maybe if you didn't understand yet what the implicit bias is, I mean, here we saw sparsity and low rank, but I mean, you have in practice you get much more complicated network structures, and maybe there's something built into the structure which leads to a certain bias, and if you don't understand it and put it explicitly, but currently it's more about understanding than trying to improve things, but maybe that comes then later once we understand.
Thank you, Holger. In the interest of time, I would ask all the other questions maybe to be deferred to the coffee break. And then as the next speaker, we have Gita Coutinhoc, also from LMU Munich, talking also about deep learning. And slides. Yes. Perfect. So Gita will be speaking about reliable and sustainable AI.
Okay, yeah, thank you so much for the very nice introduction. Thanks so much, Helmut, for the invitation. I mean, it's really a great pleasure to be here, and I think it's an amazing workshop. It's also for me nice to see a lot of faces whom I didn't see for a long time. So thanks a lot for organizing this. I think we all know, I mean, how to manage a successful AI is these days, but at the same time, I mean, we also heard through several talks that there are still problems, and here in this talk I would like to focus on two main areas. One is the problem of reliability, and the other is the problem of sustainability. And with sustainability here, I mean energy efficiency specifically. And so, I mean, certainly also because we are here in mathematics, so I would like to approach this from a mathematical side, and you will see that in a very natural way. You will then end up also in this direction and this vision of next generation AI computer. Let me see that this works. Yeah, so maybe let's take a high level viewpoint. I think we all know that we are at the beginning of the fourth industrial revolution through AI. I mean, we see our lives changing around us on a daily basis, self-driving cars, robotics, telecommunication, also very sensitive areas, I mean, which started, I think, more in the US, but now also in Germany and Europe. The whole legal system, also the job market are changed, and also there's no one area in the sciences which has not witnessed a paradigm change yet, ranging from medicine, biology, up to the humanities. So if we look ahead, AI, I think, is there to stay. It's not a hype, and we are expecting a radical change of our society during the next 5 to 7 years. But as said, I mean, there are still problems, and so let me make this a bit more precise concerning reliability. I think there are a range of problems I would like to subsume under this label of reliability. I mean, problems with safety. We all know there were accidents already by robots, and a self-driving car like a Tesla is nothing else than a robot. There are problems with security. One can hack into those systems, taking over control, modifying data slightly, so that a human would not recognize the difference, but an AI might make a radically wrong decision. There are problems with privacy. These methods are extremely data hungry, which, I mean, in many areas of the sciences is a major problem, like the whole health system, and so privacy violations happen on a daily basis. And last but not least, problems with, well, I call it responsibility. So many of these decisions are black box decisions. We don't know how decisions are reached, and also decisions often can be biased. So in that sense, I think it's fair to say that this is one major problem worldwide currently of reliability. It lacks all. So for instance, in Germany, we have the Federal Agency for Telecommunication. It is not using AI right now for critical infrastructure because the mathematical foundations are missing. So in that sense, or maybe I should put it a bit higher. So in that sense, I mean, this mathematical perspective in all those areas is extremely important. And it allows, as Holger already said, a deep understanding and then, maybe correction and an improvement concerning all those aspects of reliability. So this is one aspect I would like to touch upon. The second is, as said, sustainability in the sense of energy efficiency. Yeah? So you might have seen that on Twitter and X. Oracle is building the new gigawatt AI data center, and it's planning the 3 nuclear power plants which provide enough energy right next to it. So for instance, in Germany, that wouldn't be possible because we don't use nuclear power anymore. But I think in general, it shows a great concern for the future of AI. And so let me also show a different figure, which I think is a bit scary in a certain sense. This is from the decadal plan of the Semiconductor Research Corporation for the Biden administration. So what you see here is the world energy production plotted over time. And so now I will show you the curve of the energy we just need for communication, also over time. And so this is it. And so see, this should not occur. So within, 15 years, with the energy we need for communication, we are close or even crossing the world energy production. So if there is a limit, this is it. You can certainly do better. So here we use CPUs. If we use GPUs, we can lower the curve, but still, as you see, within 15, 20 years, with the energy just needed for communication, we will reach the world energy production, and this means you haven't turned on your refrigerator or anything like this. And so you can do better than that. So if you use novel hardware, novel platforms, and we will talk about that at the end of the talk again, you can again lower this curve, and if you're then even smarter, like here in mathematics, if we use mathematical methods, develop those, you can lower it even further. So this is for communication, this post-Shannon theory, I'm sure everyone knows. So this comes from Holger Bocher and Frank Fitzek and this group. So I think what this shows is that, going also beyond, also considering, let's say, the core, the hardware platforms with novel mathematical methods, there's a chance to also tackle this problem. So I think the general message of what I said now until now is, it is extremely important to take a mathematical perspective and view all those problems from that side. So let's start, a bit slow so that everybody's on the same level. So maybe you've seen it, but let me just still go through those slides. I would like to show you what are the key theoretical directions people are pursuing these days to understand, in particular, reliability, make AI more reliable. But let me start by saying, this is actually not a new technology. It's very old, artificial intelligence from 1943, and the key idea is to mimic the human brain. And we'll come back to that, also in the second part of the talk, because, all those models, neural networks are there. A very crude model of the human brain. And in the second part of the talk, as I said, I will show you, let's say, a bit better model of the human brain, than just a normal neural network. So this is, let's say, a custom artificial neuron, which I think most of you know. So you have, so the model is, you have these XIs, they travel through the dendrites, they might be amplified, so these are the weights. Then in the soma, the decision is reached, and this is modeled by this bias term B and the activation function rho, and then the neuron fires. And this is connected to a neural network, which is typically arranged in layers. The layers are synchronized, so everything moves from the left to the right in a synchronized manner, so time doesn't play a role here. In the second model, I will show you the time plays actually a role. And if you combine all those formulas, so this is what a classical neural network is in its, let's say, purest form. Now we have all these, let's say, fancy ways to model it, also like a transformer and so on. So this adds certain layers, but this is the purest form. Okay, so what are the key, let's say, theoretical and mathematical directions people are excited about these days? So let me just once, show you how a neural network is applied, and then, the directions will, in a very natural way, come out of there. So we have a complicated function, maybe on a lower dimension manifold. We have sample values of that at hand, and then we need to, or we want to approximate this function by a neural network. So this is our Ansatz function. And so this is already where it starts. Which architecture do we select? This is today, typically also expensive process because it's a lot of trial and error for companies. How to set the architecture, so Holger already mentioned, typically you choose it as large as your GPU. No, but I mean, hopefully you can do it much smarter than that, and you can define in a very conscious way how to set the architecture up exactly so that you fit, let's say, your data maybe the best way, and also you fit your application. Yeah, so then, I mean, you train it, and we also heard talks about that. I mean, you solve this optimization problem, so you solve it typically by stochastic gradient descent. You aim to fit your neural network function. So let's see if this works. Oh, wow, okay. So you have your neural network function here applied to xi. We want to fit your function f with a loss function. You sum over all your training samples, you optimize, and then you solve this by stochastic gradient descent. And so in the end, we know, I mean, then we get a neural network, and our performance check is then to use the test data. And so from this, I mean, just very simple flow of how you approach this, the key theoretical directions also emerge. The first is expressivity. It's maybe the most explored so far. It asks the question, I mean, which aspects of the neural network architecture affect the performance in which way. So the vision would be that for certain problem settings, like inverse problems, you can show units are the optimal architecture. Yeah? So, I mean, but until now, we don't even understand why units are the ones which are typically used in imaging sciences. Why are they the best? Okay, so now I agree. With me, it looks a bit suspicious, because now we also use transformers, but it's, so I mean, this is basically the idea to give guidelines how to choose a network architecture for particular application settings. Yeah, so then, I mean, the learning, and so there are also very exciting work in this direction. Why do you use stochastic gradient descent? Are there better, let's say, approaches? Because it's not clear yet to a full extent why this is the best. And then, I mean, this area of generalization, which sometimes called the holy grail of neural network theory, and so there we already heard, I mean, now also, I mean, the great talk by my colleague Holger about understanding of the performance of the test data set, providing success guarantees, error bounds, and as said, I mean, for instance, in Germany, I mean, federal agencies are typically hesitant to use it right now because, I mean, we have these old error bounds, but with the new, let's say, technology like AI, exactly those are missing. And so these are also exactly the three components of the statistical learning error. Then there's another area which I find very important and which also excites me, and I think it uses a lot more, could use a lot more mathematics, which is this area of explainability. So explainability now asks, I have the neural network, it's trained, it is there, maybe I bought the software, but I want to understand how it reaches decisions. And it's not only that it ensures trustworthiness. If you know how a network reaches decisions, you can also analyze whether it does something reasonable and whether it learns something reasonable. But also now in the EU, at least we have the EU AI Act. So and every AI technology has to comply with that. And explainability is in it. So there's the law or the article to write, the right to explain, that every AI technology has to come with an explainability approach. So in that sense, I mean, also for, let's say, legal reasons, this is a very important area. And as said, I mean, from my viewpoint, I think it deserves also a lot more theory. So here now, what I would like to first do in the first part of the talk, I mean, we also have a lot of work on generalization, so we work on the section of graph neural networks. But, I mean, there were already many talks now on generalization, so I would like to, in the first part now, focus on explainability, show you how we set that up, I mean, also from a mathematical perspective, so that we can prove also something about the algorithm in the end. And then in the second part, I would like to dig even deeper, more maybe to the core, and then we will come also to the point, and what I also advocate, that we also not only need to rethink, let's say, the software part, so the algorithm, improving those, but also take the hardware components into account. Yeah, so that's the plan. So let's start with explainability. And maybe I can whet your appetite to also go a bit more in that direction. Okay, so yeah, so let's look at, let's say, from a mathematical perspective, so that we also, let's say, have a bit more understanding of what happens there. So explainability, I'm sure you've seen these pictures. Yeah? I mean, so you want to understand decisions of black box predictors. You have here, let's say, this 3, and the network correctly says this is a 3. And so then, I mean, these algorithms output this relevance map, and which basically kind of says, Okay, so the red dots indicate which pixels the network took most into account for the decision. Yeah, and so here it makes a lot of sense to look at these openings because that distinguishes a 3 from an 8. Yeah, so that is reasonable. Now, here's a funny example, or actually maybe scary example. Yeah, so from my colleague Prof. Robert Müller when I was at TU Berlin. So here, the network was trained to recognize horses. And so then the explainability approach, so it correctly says this is a horse. And so this is what the explainability approach shows. Yeah, so what does it show and what happened? Well, the network was wrongly trained. It was trained on biased data. So all the horse images had a copyright tag. And the network did the smartest thing it can. Yeah, so let's say learning the structure of a horse is extremely complicated, but learning a copyright tag is very, very easy. Yeah, so the network only looked here to recognize that this is a horse. So if you now have an image, let's say, of Wolfgang's car, like an Audi TT, with this copyright tag, it would say this is a horse. No? Which is maybe, I don't know how you think about it, Wolfgang, but yeah, many horse, yeah. So it's still a horse, okay. So it would do something reasonable. Okay, so yeah, so this is basically, one thing you would like to understand with explainability. You also, for instance, in medical sector, because there, you train on huge data sets. And sometimes there, if you then use these explainability approaches, you might even find structures which a human would not have seen before. So you could also detect something new maybe in the data. Yeah, but the question is these relevance maps, what is it from a mathematical sense, viewpoint? We like also to talk about optimality. So also this is a bit on a shaky part. And also why should pixels be important? Why not maybe combinations of pixels in a very natural way? And so that's where the field is going. You aim to communicate with the AI like you would with a human. So it's out of which, to a certain extent, at this point, with experiments we are much further there. But still, from my viewpoint, what is very important for me is if you use now all these, let's say, approaches to ensure trustworthiness and reliability, what you need is that the explainability approach itself is also reliable. Yeah, and so I think this is a lot swept under the rug. People like these fancy images, but it's not really clear what happens. So now I would like to show you one approach which we developed. Yeah, I don't want to claim it's the best or so, but it is on a mathematical foundation, and also then we can, in the end of this part, I would like to show you one concrete mathematical result where we can prove something about this approach. Okay, so it comes from information theory. I thought Helmut likes that maybe. So rate distortion, viewpoint. Sorry if I simplify this very much. Yeah, so the idea is always that you have two persons. They are always called Alice and Bob for some reason. Alice has a message. She sends parts of the message to Bob. He decodes it, and he will make an error. Yeah, and so the rate is how much is sent. Yeah, so the smaller the rate, the larger the error, the larger the distortion. Yeah, so it's a trade-off. And so now you can phrase this explainability approach in this framework. You have here your, for instance, neural network. So Alice and Bob both have the neural network. Alice has the original image. She sends parts of the image, hopefully the relevant part, to Bob. Bob needs to first bring it back to the image size to not distort the meaning. Maybe he obfuscates with random pixels, which maybe is the safest thing to do in a certain sense. He puts it back in his neural network. He will get the message basically out, and he will make an error. Yeah, and hopefully, these are the relevant part. So the more this is the relevant part, the closer this distortion is. Yeah, so and now, how does it look? So this is the distortion. So you take the expected value of phi of x minus phi of y. And what we aimed for was conciseness of explanation, sparsity. Yeah, so to have, let's say, very few bits in some sense. And so this is then also the rate distortion function, which aims for having very few pixels here, but keeping the error, the distortion under control. And so, all of you will say, who works in optimization, this is not feasible to compute. So this optimization problem you cannot solve. And that's true. So we can show that this is NP-PP complete. So even approximations are NP-hard, and so now following, Holger already gave a talk about compressed sensing. Following this relaxation idea, you can relax And so this is then what we solve. What, let's say, our first idea was. We will see that we improved that significantly. So you have here the distortion. You have here now exactly like compressed fencing. You relax from the number counting the number of pixels to the L1 norm. And you put a relevance score on every pixel, and you have something to balance between the error and the sparsity. And so, I will show you that. I said we can do rigorous mathematics with this indeed. But let's start with a couple of images just to give you a feeling of that. So you see here, you have here the original image. The network said this is a dog, and so these are explanations. And you see here, ours is tuned towards sparsity, and the structure of the head of the dog is very much outlined. So in a very concise way, so this supports this, let's say, idea, what I said, that we want to have concise explanation, very precise. You can also then compare, and so the way we compare here is, so you have here the rate, the number of important pixels, versus the distortion, and ours, actually not surprisingly, because it's tuned towards that, so behaves here the best. And now you will say, this is actually a really unfair comparison, because our algorithm is tuned towards that. But then if you look at the other algorithms, and if you look how they compare, they actually use something similar, because they line the relevance of the pixels, and then they start flipping at some point and see when the decision changes. And that's exactly so this rate versus distortion. So it's a bit strange, I think, that people use, let's say, a measure for comparison, but don't really optimize for that. Okay, so then, we actually improved that in two ways. First of all, these obfuscation look very strange, so we used what's called an in-painting gun, so a generative adversarial network, to fill this with a bit more, let's say, meaning, in a certain sense, to make more realistic pixels out of these random pixels. But maybe the most important one, and maybe this also alludes to many people here in the audience. So what we then did, instead of using pixel-based explanations, we used decompositions using applied harmonic analysis, like wavelets or shearlets, and then put the relevance scores on those pixels. And so this we called, for instance, cartoon X. And this has a nice comparison with image compression. Because, so image compression, weighted compression, just, in a nutshell, you have your original image, you have your weighted decomposition, you select the largest entries, you replace the others with 0, you reconstruct, and then you hope that these are close. So that's all known to us. This cartoon X, which we introduced, is a bit in that spirit. So you take the original image, you do computer weighted decomposition, or shearlet, or whatever you take here. What's your favorite? Let's say XLET. You select the largest entries, you replace the others with now random noise, or with in a more natural way. You reconstruct, and then this is never close to the original image, but that's also not what you want. You want that if you look through the lens of the neural network, then these are close. So in that sense, it's a bit in that spirit of compression, so you can also use some tools from there. Okay, before I show you this result, one of the results which we derived, let me also show you a couple of examples which we computed. Two types. One is how you can recognize or analyze whether a neural network maybe had something wrong, but also how you recognize that the network did something wrong. Okay, so the first comes from also in honor of Helmut from telecommunication. So this work with a group of Giuseppe Caire. So here the network computes the radio map. You see here the buildings, the blue parts. The red dots are cell phone users, and here's the cell tower, this wide area. And the network now computes this black and white background, which indicates everywhere how strong the signal is. So this is the radio map, and so here the signal is really bad, which makes sense because there are a lot of buildings obstructing your view towards the cell tower. But if you're standing here, you have the cell tower in your line of sight. But for some strange reason, the network outputted here an area of bad reception. And so now you can ask, did the network do something wrong? What went wrong with the training? And so you can ask, why did you compute, let's say, this area in this green part? And that's the explanation. And now if you look closely, I mean, indeed, these cell phone users have not that great reception, not as good as reception, if you take into account that they actually should have that in line of sight. Yeah? So there's something else going on, and we found out that actually the data was faulty. There was a building missing in the city map. So in that sense, I mean, the network did something correct, but yeah, I mean, you could not see that immediately the data was faulty. So that's, in a way, understanding seemingly wrong decisions. You can also understand wrong decisions, and there's a kind of funny example. So here, I mean, the network for some reason decided this is a diaper, yeah, so a Windel. Yeah, so although obviously it's a man with a dog, and so here the network decided that this is true, although it's a man carrying something. And so now I will overlay this with the explanation, and you can see what the network has seen to reach that wrong conclusion. Yeah, so I will put it on top. Yeah, and so here, I mean, it looks a bit like a baby, and the diaper is not far off, and I mean, you can mistake actually this sweater for a screw. And also in that sense, I mean, once you find that out, then you can counteract, you can retrain the network and improve the performance. And we then extended that also to shearlets. Well, maybe, I mean, those who know me, maybe in a natural way, because, I mean, these are very dear to my heart. And I said I wanted to show you one mathematical result. So here we realized that, I mean, there's a kind of consistency problem for some explanations. So here, I mean, you have, let's say, the original image, you have different explanations here. And we looked at the line structure, the curve structure. Yeah, so the edges. And what you realize is, I mean, here, this is a subset of this edge structure, but here the network invented something. So it's not, I mean, the edge structure is not really consistent with the original data. And so this can certainly also then distort the meaning. So if the explanation is very strange, I mean, it's not consistent, I mean, this is not what should happen. And so this is basically something which we could also rigorously, for instance, prove. So we have an image, and we have basically, so this is the original image, we have the y, which is then the explanation, and we could show that the wavefront set of y is always a subset of the wavefront set of x. So that means, so if you do that in shearlet space, that means that this is always, I mean, a subset of this, whereas other explainability approaches do not have, let's say, that type of reliability. And so this, I mean, I would wish is a bit more in the direction or in this field, and right now I said it's maybe a bit more on the, let's say, shaky feet, so that algorithms look nice. But also, I think I had this discussion with Wolfgang also once, it's also very difficult because, I mean, this field is highly interdisciplinary, so what is an explanation? Okay, so let's conclude this part, but maybe since I just talked about explainability, let me add maybe 2 or 3 more slides in this direction, because now, I mean, I talked about the EU AI Act, so what is an explanation? We have one example now about what to use for the EU AI Act. And so let me also add here one point where I also think mathematics can have a huge influence. Because I'm sure, I mean, you also discussed with many of your colleagues, we have these requirements of the EU AI Act, we have here the right to explanation, and there are current dangers in particular, I mean, for Europe in general. So if you compute worldwide, now, I mean, small-size companies, startups, I mean, have this disadvantage as they have to go through that. On the other hand, I mean, you know, if you look at, for instance, the term of privacy, the legal term, there's a mathematization of that. So differential privacy, so this is not up to interpretation. So know exactly what happens, what you need to check your algorithm with respect to. So together with Holger Boche, we did that, for instance, also for algorithmic transparency, developed a mathematization in a way for that. And so now, I mean, and again, I don't want to spend too much time on that. So now the idea is to a certain extent, formalize the legal requirements of the EU AI Act to which extent this is possible, and then ideally to develop a system for automatic verification, which would be then, I mean, if you can do something in that direction, would be very fair, very low cost. And so there's now also from the Bavarian State Ministry for Digitalization, say, a research project which I'm heading, joined with colleagues from TUM and the TU Nuremberg to go in that direction. And so just, I mean, to conclude that part, so together with Holger Boche and a PhD student of mine, I mean, for instance, we have results now with this definition of transparency, which we introduced, equivalent conditions. And I think the key point here is that, so there's also, let's say, the computability part, which I will talk about later on, a bit more, also comes into play. Now, but then, I think the main point here is if you have this mathematization of legal requirements, then, let's say, you stand on solid feet, and you can do much more, and also can help, let's say, small, medium-sized companies. Okay, so now, as said in the second part, I would like to delve a little bit more to the core of reliability and sustainability. And so what do I mean by core? So core going beyond, let's say, the software part, going also to the hardware. Because computing is the heart of modern technology. As you see, it's used, and it's actually the basis for all of these, let's say, great developments which we see these days, digital transformation, Gen AI, virtual reality, and so on. So it is the heart of that. And so the question we then ask ourselves is, are there maybe limitations we do computing these days? Do we go beyond that? And so what is the problem, how we can solve it? And what I would like to advocate here is, if you really want to have sustainable and reliable AI, there is a need to also rethink the way we do current AI computing. So to dig deeper in such things. Okay, so are there fundamental limitations to be aware of? So right now, we all use digital hardware. Everyone who has a laptop in front of you, so you have digital hardware in front of you that's modeled by a Turing machine. And there's this notion of computability, a beautiful theory of computability, which basically says a computable function is one for which you can compute this input-output relation on a digital machine for any accuracy. If something is not computable, maybe that's not that great, but you can still put it in your computer, in your laptop, but then you have to live with that you might have a problem with reliability, you don't have any theoretical guarantees. And so what we could show is that, indeed, for certain problems, there are these issues. So, for instance, for a solution of fundamental inverse problems, could show this is not Turing computable by a neural network, but also in general. So here's the precise result. Holger already and others already introduced L1 minimization. So what we looked, for instance, at is, this very classical problem of L1 minimization to solve an inverse problem. And then we showed, we cannot find a Turing computable function which approximates the, let's say, the true solution set even up to 1/4. So, certainly if you're in a special situation, you have very special accuracy. In these situations, you can always do that, but there is no general approach. That's here the point. That this is not Turing computable. And so 1/4 is also, maybe far off machine precision. So this points towards a problem, and in fact, we could show many other results of this type. So for classification problems, pseudo-inverse, also to a certain extent PDEs, that you have what's called a complexity blow-up, so that the size of your input, is exponentially increased during the algorithm, and also optimization problems. So this points towards, doesn't need to be, but it points towards the problem that one might need to rethink the hardware to maybe even gain more reliability. Okay, so that's not that great, but so if you dig deeper a bit in mathematics, there are other models besides the Turing machine, in fact, analog models. And so one is, for instance, the Bloom-Schutz-May machine, and so there you can show that then things become computable. And so this, I think, points to a very exciting direction, that it might be also, as said, the hardware component, so going from digital to analog, which I think for people from electrical engineering might be a bit strange, because now you go back. First you went from analog to digital, and now you question again the digital side. But as said, for instance, the computability results show that also. So if you think about that, from a high-level viewpoint, if your laptop crashes, you turn it off and you turn it on again. But with your human analog brain, that would be actually devastating if you need to also turn it off, turn it on again. So the analog has much more possibilities. So I think that's the message. And in fact, there are exciting directions. Neuromorphic computing, which is closer to the human brain. So you'll see, some mathematics also in a moment about that. Biocomputing computes in living cells, and there's also quantum computing, and so on and so on. And I think what is also exciting here is that, for instance, neuromorphic computing is in addition also considered much more energy efficient. So being the idea that the closer you are to the human brain, which loses much less energy than a, let's say, a gigawatt computing center, you also gain this energy efficiency. And so the idea is reliable, sustainable AI, also by next generation AI computing. And let me also add here a personal remark. I mean, we also now founded a company in this direction, ecologic computing. I thought I would never do that, but I mean, with two colleagues like Holger Bocher and Frank Fitzek, we started that in June. Okay, so let's now delve a little deeper into next generation AI computing, and then I'd also like to show you a bit of mathematics, which we did. Okay, so this I think we all know, it's a von Neumann architecture. We have binary inputs, binary outputs. The neuromorphic architecture is a bit different, so you have a spike train as an input, as an output, and then the architecture itself is kind of also like a neural network already, so with neurons and synapses. It's considered closer to the human brain, more energy efficient, the execution speed also higher, and maybe at some point also robustness. Concerning energy efficiency, I mean, there are already, numerical experiments to show that this is in fact true for many problems. Now, the question you can ask is, since we talked and also heard a lot of amazing talks about neural networks, so what is the correct type of neural network now for this new type of hardware and new type of architecture? And in fact, this is not such a huge question, because the architecture itself is like a neural network. And so the correct mathematical definition, and I will show you the definition on the next slide, are so-called spiking neural networks. But maybe let's give you first an intuition in what these are. So you have your image, you encode it, and also there I have to admit, people do a lot of heuristics there. Also there the theory is still missing. So there's a lot of ad hoc, let's say, encoding of an image or of data into these spike trains. But in any case, then these enter the neural network, and what is key here is this neural network, and therefore I made the point in the beginning, is not synchronized. So every neuron acts on its own. So for instance, this neuron, which you say here, N3, it will get some inputs at different time points, and it's building up a potential. Each time it gets an input, it goes up, then it goes down a little bit, then it gets the next input, and so on and so on. At some point, it will reach a threshold, and then it fires. So everything is very asynchronous. So that means time plays a huge role here in this, and so you can also encode information in a certain sense in time. It's more biologically realistic, because in our human brain we don't have these very strict layers. From a mathematical viewpoint, it's actually, exciting, but also much more challenging, also because there are actually numerous models for spiking neurons. For instance, the spike response model, and so on. So it's also difficult to decide which model to take, because people use this in a very heuristic manner. There's actually not that much theory. We also wrote a survey paper about spiking neural networks. Okay, so I would like to show you some, let's say, the model and some results on expressivity, and maybe, so I think you all know this. Expressivity you can view in two different ways. You have function approximation, and you have the number of linear regions. So these are two ways to analyze expressivity of normal neural networks, and so our goal was to compare spiking neural networks with classical neural networks. Okay, so what is the spike response model? So let me walk you through that. We have a directed graph that's like a normal neural network. You have some input neurons, you have some synapses, you have weights on those, that's exactly the same, but then you have a delay. So time is an issue here, so the delay on the dendrites, and you have the response function. So then every neuron itself, which is not in the input set, has a threshold, that's the bias. So this is similar, but then it has this potential, which is slowly building up over time, and each time it gets an input, and at some point it reaches this threshold. So the formula, it's building up. You see here. So what you see here are, so these TUFs are the times, or the firing times of the neurons which are connected to that, which give input to that. So this is also, this is this term. Then here you have the response function, you have the weights, and then you basically sum over all the neurons which give input to this output neuron, and also those connections. And so we do that over time, and at some point this will reach the threshold, and then it drops down again. So that's one of many, many models. And so here, for instance, we looked at if you emulate a normal neural network by a spiking neural network and vice versa. So what you realize is maybe also not that surprising. So if you have a normal neural network and you emulate that by a spiking neural network, what you would expect also happens. I mean, a spiking network is more flexible in a sense, so you just need a linear number of neurons, linear number of layers. To emulate that, vice versa, becomes more difficult. So if you now have, let's say, a spiking network, and you want to emulate that by normal neural networks, so you need here, I mean, you see these exponential terms. Now you will immediately say, do you have a lower bound? And I have to admit, I wish, but I mean, in some cases we have that, but we are still lacking, let's say, this overall result, which shows that for certain general, let's say, function classes, you cannot do better than that. So, for instance, I mean, for functions like the minimum function, you can do the calculations and you can show that, in fact, I mean, here you just need basically a single error for that accuracy, whereas the normal neural networks need to have at least step 3 for approximating, let's say, the minimum function in that way. So these lower bounds are extremely difficult. As said, I mean, this whole theory is very, very challenging. But I mean, at least in these cases, you can show spiking networks are, in that sense, strictly more expressive. Something similar happens for if you, let's say, count the linear regions in which this neural network tiles it. So here you get a bound, which, I mean, in many cases is also tight. So maybe not going too much into the details, we can show for some cases this is a tight bound. But again, I mean, I wish we would have a more comprehensive result showing that for some, let's say, function classes, large function classes, spiking networks are strictly more expressive. So then, I mean, I said there are other models. I would like to show you also a different model to show you a bit the complexity of this whole field of spiking neural networks, which is also actually not new. So it's also old, but now I think the difference to now is that now we have this neuromorphic hardware, so we can use that, and we can effectively, let's say, compute things. So here, this is, for instance, the so-called discrete leaky integrate and fire model. So you see this is very similar, directed graph. We have, let's say, also synapses with synaptic weights. We have the firing threshold, but then, I mean, there's also a leaky parameter, which is a bit like the delay, a latency, a spike sequence. And then here again, I mean, we have this membrane potential, but now things are a bit more complicated and maybe modeled also a bit more biologically realistic. You see these coupled equations where now basically, I mean, the membrane potential is set into relation to the spiking sequence to act also in particular. If it's set to 0, it's not set to 0 completely to a certain extent. And so this makes things more difficult. I mean, there are also very general models using stochastic PDEs, which are basically on top. And so you can ask, I mean, to which level do you get more and more biologically, let's say, realistic, which makes then the analysis more exciting, but also extremely challenging. And, I mean, one has to admit that, I mean, I think in neuroscience, people know to a certain extent how a neuron works, but, I mean, also this whole combination of neurons in the brain is still, I mean, a lot under investigation. So but I think these two fields can work a bit more together. And also here, I mean, let me also again just show you a couple of results. So here we, for instance, analyzed also, again, I mean, the expressivity analyzed. If I have now this, let's say, the spiking neural network where we use this different model, we can show optimal approximation results, depending also on the number of neurons which we use. So for us, I mean, next steps are also to look at dynamic settings, not just static settings where, I mean, input-outputs are time sequences. And you can do similar things for the linear regions, also estimates. Let me not go too much into the details. Again, I mean, you get precise bounds, and you see, for instance, here the latency parameter appears in here, whereas in here, but I think what maybe makes it a bit more visually appealing is, so here you can look at these pictures, and one key difference is that the number of linear regions this input space is tiled into does not scale with depth and number of layers, which is very different from a normal neural network, which scales with depth, where the number of linear regions scales with depth. So, for instance, we do Montefiore and so on. I mean, Also, Sarah van de Geer have results on that for normal neural networks. So here it's a bit different. Yeah, so here you see that for deeper neural networks, these regions somehow merge together, which is actually not a bad idea because then, the functions become a bit more smooth. But it's not really clear how and what effect that in the end has. Also, there are other phenomena. For instance, if you now go to, let's say, more depth, then now if you change, let's say, this latency t, then what you observe is that somehow not just lines are added, but always these parallel hyperplanes. And there you observe now a polynomial increase of the number of regions as opposed to exponential increase for normal neural networks. So there's something else happening, and it's still, not clear. I think maybe expressivity is just one very precise, one of many viewpoints you can take. The direction we are going right now is basically also to compare the energy efficiency. Model energy efficiency and then see for which classes one is better than the other. And so this is all part of a large-scale project which I'm heading. It's set up between both two states in Germany, the state of Bavaria and of Saxony. And so the idea there is to go about it from a mathematical viewpoint, to derive a framework for green, reliable AI, so that for large application settings, you can say exactly, so these are the optimal hard-software combinations which you want to use, and these are, let's say, the AI approaches, AI software, so that you get maximal energy efficiency and trustworthiness, and so these are some of the applications we anticipate, and Holger Boche is also, he's responsible for the team's work. Okay, and so these, I also would like to thank my team there, for the project GAIN, who are now working in this direction. Okay, so let me conclude. Don't worry. Let me conclude. So, as said, and I hope you agree, AI is amazing, but there are still many problems concerning reliability, sustainability, and it's extremely important to take this mathematical perspective, because only then you can understand things from the depths, and then, let's say, improve the algorithms, improve, let's say, the error bounds. We then also, I showed you a little bit explainability, aim to whet your appetite also, to maybe also delve in that area. There are problems also with digital hardware, which I also alluded to a bit. And one idea is to go to analog hardware, to analog AI systems, to achieve mathematically reliable and sustainable AI. And so with this, I'd like to conclude, and thanks for your attention.
Thank you very much. Yes.
Quick question, these neuromorphic analog hard systems and also spiking neural networks, how do you train them? Do you train them using the same methods like stochastic gradient descent and so on?
Yeah, that's an excellent question. It's actually not clear. I think the community is also not, let's say, that much focused on one method right now. Let's say the easiest you can do is you can transfer to normal neural network, train there and move it back, which I think is not that great.
No.
There are surrogate models and surrogate methods. But yeah, so this is also open to a certain extent for good optimization. That's one of many, let's say, theoretical problems.
Yes. I hand over to you.
Yeah, thank you, Gitta. Maybe I misunderstood a comment on one of the last slides. Maybe I misunderstood, where you said that in the spiking models, they tend to merge regions, linear regions. But that does seem to be a contradiction to the larger expressivity. Because if you have large regions of very simple structure, that can't be as expressive as a much more refined setting.
You are exactly right. So I think there are a lot of things which we don't understand. So what I said is, we have before, I showed you these results of we emulate one neural network by the other. Yeah, and so we have these results, but we only for certain cases we have these lower bounds. Yeah, so it could be that there are also cases where these are actually not that much more expressive. So maybe even, not worse, but not even expressive. So what we would like to have is, for large function classes, they are more expressive, and then I believe then also these, let's say, these patterns show them. I should say, also the second part was for a different model. Yeah, so one was the spike response model, one was this leaky integrate infier model. Yeah, so it could be that also, the model make a huge difference, and so in one model it could be maybe more expressive than the other. So this is, I think, I wanted to point out. Also, this is, an area where I think mathematics has a long way to go. Yeah, it's important, but you are absolutely right. This contradicts a bit the result from the spike response model.
But the general complexity bounds, they all show an exponential dependence on the dimension, right? So this is kind of haunting you, like this is what you want to avoid in a way, but you seem to be in there generically. So, and maybe one last question concerning these computability models. There is no computability model on the world which is reality. So now, what do you do if one computability model contradicts completely what has been proven in another model which is extremely close to engineering? So what are you doing then?
Nothing is perfect. But these
Yeah.
maybe I should say, I think the Turing machine itself. Yeah. Okay. So the computability model, I think. So first of all, I think the Turing machine, to a certain extent, is considered very close to reality. Yeah. So that I would not doubt. But I should make the point, and I think I also mentioned it. These computability results are for very universal methods. Yeah. So typically, if you are in numerics and you see that things work, these are methods which are specifically designed for some, very precise problem with a very precise accuracy. So these are more showing that you have to be a bit careful with very universal methods which you apply to a large class. Yeah, so this is, I think, what these computability results show. They are...
Well, okay. But that now becomes a philosophical question. Because you could say every continuous function can be approximated by the Bernstein method with the polynomial approximation. Every continuous function can. That's the highest universality you can think of. You would never do it because it's most of the time the least performant method. Okay? And in large-scale computation, which arises in real applications, I think there's never a universal method that you apply. But you always apply something that works very well for a specific problem. A solver for an elliptic problem is always totally different from a solver for a hyperbolic problem. And I think there's no way to overcome this. So do I understand correctly that you are saying basically if you want to apply one method to all of these different problems, then you are bound to fail? That I believe immediately. But what else do I have to conclude from it? Because like the Poisson equation, that's the fruit fly numerical analysis. That's the easiest problem you can ever come across. And which is, you see, so that irritates me. If you come up with the conclusion to say this, you can't compute. Okay.
Yeah, I think that the point here is that these results point towards that digital hardware might have restrictions because, you can show with analog hardware, you can do, let's say, better. It doesn't mean that all the algorithms don't work. Yeah, so it means, as said, and that's what you say, so these universal type methods, these have a problem for, let's say, the digital domain, but not for the analog domain. Yeah, so what you bring out for you, is, I think, up to everyone. But I think for me, it shows, analog methods are more powerful in that sense. And it could be that this is also one reason. Yeah, but I wouldn't say that, digital hardware is not usable. Yeah, and in fact, the way, the direction we go is also, certainly the idea is to augment digital hardware by analog hardware, maybe for certain problem settings where you need a bit more flexibility. Yeah.
I think there was another question, but in the interest of time, if it's no longer the case, then let's move to the coffee break and thank the speakers again. So we reconvene at 10 past the boss has had. Okay, it's my pleasure to introduce the next speaker, Amit Singer from Princeton, who will talk about the mathematics of chiral electron microscopy.
Okay, thank you very much. So thank you very much for the organizers for inviting me for this great workshop. So indeed I'll talk today about the mathematics of chiral electron microscopy. And perhaps my goal today is to give you, first of all, a very brief introduction for what is chiral electron microscopy. I'm sure that not everyone here knows about it. And no worries, you don't need to know biology or anything. It's targeted towards you, the mathematicians. And my goal is really to convince you that it's really a very rich mathematical topic that many of you are then welcome to dig more into it. So what is a single particle chiral? So this is a technology for determining three-dimensional structures of biological macromolecules at a high resolution. And the way it works is very simple. You prepare a sample of your molecules, and then you freeze them in a very thin layer of ice. So it's so thin that if you look at it in the vertical direction, you'd see at most one molecule. But there is just no room for two molecules to be one on top of the other. And then you shoot an electron beam. So it's the electron microscope perpendicular to the specimen. The electron beam would go through the ice layer, through the molecule, if there is a molecule there. And beneath you have a detector. In the old days it was film, now it's like much more sophisticated cameras. And to first approximation, for the sake of the talk today, just think of it as tomographic projection images. Okay, so what you measure is basically the integral in the direction of the beaming electrons of the, let's say, the scattering potential created by those molecules. And so what you see on the left here is just it's just an artist concept. These are not real molecules. Just to illustrate for you the imaging process, you obtain an image like this called a micrograph. It has several projection images. The first step is usually just to do image segmentation and to what is called particle picking to find where the particles are in the big noisy micrograph. In reality, the noise level is much higher, that even particle picking can be difficult. And so the reconstruction problem is how to go from multiple micrographs that look like this, tomographic projection images, and find a 3D structure. Okay, so it's an inverse problem. What makes it difficult are two things. One is that we're dealing with very high noise level environment, and I'll show you experimental images in the next slide. And the reason being is that the imaging process itself is destructive. Basically, the electron beam has so much energy that it breaks down the chemical bonds that create the molecule, and so you cannot apply too much radiation damage to the specimen. And the other difficulty is the unknown poses of the molecules. So unlike the cousin of this problem, which like the medical imaging problem, say CT reconstruction, computerized tomography, in which the patient is being told, say, to put still and not move for the duration of the imaging process. Here we cannot give the molecules instructions. Okay, so every molecule just picks some random orientation, and so the viewing directions are unknown. Okay, and that makes the inverse problem much more difficult to solve. Okay, it's no longer a linear inverse problem. Okay, so to give you a sense of the noise level, I'll just show you on top two images from a much larger collection of about 17,000 images. At the bottom, two images from, again, like a data set of about 100,000 images. And remarkably, even though they're so noisy, people can still get very high resolution reconstructions out of them. And so what's the magic going on here? The magic is that you have very large data sets, and so there is some very clever averaging going on that somehow you average out the noise and remain just with the signal. And I'll try to explain today how this magic works and what are the limitations. So over the last, say, decade and a half, there was a major improvement in the resolution that can be obtained with cryo-EM. This has been coined the resolution revolution. So it's just, again, like an artistic picture to give you a sense of the improvement in resolution over the years, say from the very blobby reconstructions on the left, say 15 years ago, 20 years ago, to what was achieved just like, say, 10 years ago, and now we can even get to atomic scale resolution. And because of this improvement, the Nobel Prize in Chemistry in 2017 was awarded to 3 of the pioneers of cryo-EM. For those from EPFL, you may be familiar with the first name. Yeah, but it's really a technology that has been around for more than 40, even like 50 years. But it's really because of the improvement in resolution that now it's competitive with X-ray crystallography that the Nobel Prize was given fairly quickly after the resolution revolution. And you also see the revolution in terms of the popularity of cryo-EM. So here is so before my flight, I downloaded this statistics from the PDB, from the protein database. So it shows you in logarithmic scale the number of protein structures that have been deposited to the PDB over the years. And you can see that, okay, so in yellow you see the cryo-EM, and you see the exponential rise, okay, so this is in log scale, whereas X-ray crystallography more or less plateaued over the last few years. So people even predict that in a few years, actually, X-ray is going to take over, cryo-EM is actually going to take over X-ray crystallography. The dip that you see in 2025 is just because we are in May, okay, so the year is not over yet. And it's not just the number of structures, it's also the importance in terms of both biology and just, like global health. So, for example, very quickly in the beginning of the pandemic, so this is a science paper for March 2020. So early on in the pandemic, the 3D structure of the spike protein of the coronavirus was determined by cryo-EM, and this aided in the development of vaccines and therapeutics. Actually, the structure was even like maybe a month or 2 months before March, okay? So very quickly, so you see that the advantage of cryo-EM that because you don't need to crystallize, you can very quickly get the structure. So that's the structure that you see like on the news and the New York Times. And okay, now that we have so many structures, okay, both by X-ray crystallography and cryo-EM, and maybe this connects to other talks that we've heard today and yesterday, you can train deep neural net methods on all those 3D structures. And so last year, the Nobel Prize in Chemistry was awarded to basically people who develop such architecture for protein structure prediction, okay, directly from the sequences, basically solving what is called the protein folding problem. Okay, so you can ask me, okay, so why do we need to do now more cryo-EM experiments? Okay, but okay, it's not. First of all, it's not completely accurate. It has issues, especially if you have heterogeneity that I'll talk about later on, and other complexes and so on. But again, you see how doing a lot of experimental and important science then leads to more, like much more capabilities in terms of computers and so on. Okay, so I need to tell you a little bit now about the math. So how reconstruction in cryo-EM is being done. So first I need to tell you, okay, what's the forward model before we solve the inverse problem. So the forward model for simplicity today is very simple. You have the unknown 3D structure, okay, let's call it phi. So phi is just a function from R3 to R, a function of x, y, and z. Let's say the electrostatic potential at any given point in space created by this molecule. And the images are obtained by first rotating this phi by an unknown element of SO3. Let's say that I know how to center the images, okay. And then you just integrate it in the direction of the beaming electron, say the z direction, and you obtain an image of X and Y that you also contaminate with noise. And then the basic reconstruction problem is how to go from n such noisy images and estimate phi. And there is an even more complicated problem, okay, where we no longer assume that all the particles in our sample are identical in structure, but actually we can have an heterogeneous population. So some proteins, actually most proteins, they can fold, okay, and they deform, and they can bend, and do all kinds of motions. So not all molecules have exactly the same structure, and so instead of having just one phi, there can be, for every image, there can be a different phi. So basically the phi's are sampled from a distribution. And what we'd like to do in this more complicated inverse problem is to estimate the distribution of phi from the images, okay, and not just a single ridge structure. And I'll get to it later on. Okay, so how do we go about solving this problem? So if there is anything that you have to take from my talk today, this is the one thing, okay? If you haven't heard about this before, that's like the take-home message, okay? This is the Fourier projection slice theorem. So it's like a tomography 101. And what the slice theorem says, it gives you a really nice relationship between the Fourier transform of the 3D object that you image and the 2D Fourier transform of the projection images. And the relationship is simply says the following, that if you have an object, okay, in real space, and now you take a tomographic projection image, so you get a 2D projection image, and now you take its 2D Fourier transform, then this 2D Fourier transform is nothing but the restriction of the 3D Fourier transform of the object to a planar slice that goes through the origin in the Fourier space. And the rotation of this slice is exactly the rotation of the molecule of the object. Basically, it's just the slice that is perpendicular to the viewing direction. And so in medical imaging, because the patient is not moving, okay, so you know exactly, the machine, let's say, know exactly which projections, okay, how to populate those projections in 3D space. And then after all of them have been located and inserted into the Fourier space, then you can do 3D Fourier inversion and get the object back in real space. But in cryo-EM, because we don't know the rotations, we know that we get very noisy slices, but we don't know where to place them. Okay, so that makes the problem more challenging. But luckily, we have geometry to our help, and so we know from, I don't know, elementary school or high school geometry that every two planes in R3 will intersect at a line. Okay, so now it gives you some consistency relationship based on which you can actually solve the cryo-EM problem. Meaning that we know that any two projection images, even if I don't know their viewing directions, I know that if I'm going to take the Fourier transform, let's say on a polar grid, there must be one radial line in the Fourier transform of one image and one radial line in the Fourier transform of the other image, let's say the red lines, on which the values of those Fourier transforms agree. Why? Because they correspond to two slices, and those two slices must intersect at a line. And on that line, the values of the Fourier transforms must be the same. So with clean images, I can find, let's say, just by brute force correlation of all the lines in one image with all the lines with the other image, I can find this common line of intersection, and this would give me a lot of geometric information. Basically, it would tell me, okay, I know where those two planes intersect, so out of the 3 degrees of freedom of SO3, let's say the Euler angles, I know 2 out of the 3, I just don't know the angle between the two planes. So what do you do to determine that angle? Well, you just insert a third plane. And so now everything becomes rigid. So from the common lines between 3 images, you know, you can basically find the relative rotations. So this was discovered more or less independently in the mid-80s in the East and the West, more or less simultaneously. It's known as angular reconstitution. It works very nicely with clean images, but unfortunately with noisy images, you're going to misidentify common lines. And then the question is how to come up with algorithms that will be robust to noise. And so I and others, we worked quite a lot on trying to come up with algorithms to do that. My talk today is not about this, but if you're interested, we came up with better common line approaches using semi-definite programming and synchronization of rotations. You can also try to improve the SNR, okay, to denoise the images by what is known as 2D image classification and averaging. Basically finding for every image other images that look similar to it, and therefore you think that we're taking from similar viewing directions, and then average those and boost the SNR in that way. And so this kind of paradigm definitely works for, especially for large molecules where the SNR is not too bad to begin with. But, and we've done many reconstructions using this, but today I actually want to talk about the other extreme of small molecules, where the SNR can be very low, and then I want to convince you that it doesn't matter like how sophisticated the algorithm is going to be. There is actually a fundamental limit here, is that you cannot estimate rotations when the SNR is too low. Okay, in the sense that even an oracle would not be able to estimate rotations. Why? Because let's say that, I don't know, Peter is an oracle, he knows the 3D structure of the molecule, and what he will do is basically generate clean projection images of the molecule, and then he will just try to match them with the noisy experimental images. But because the experimental images are so noisy, regardless of which metric he's going to use, let's say even if the noise is wide Gaussian noise and you're just going to use some, let's say, correlation or Euclidean distance, then there will be like huge fluctuations in the correlation values just because the images are so noisy. And you'll just make a lot of mistakes in assigning the rotations. So even if an oracle that knows the 3D structure cannot estimate rotations, you cannot expect me to come up with some wonderful algorithm that will be able to estimate rotations. Maybe we'll keep the questions to the end, so yeah. But yeah, keep your question, because I might answer your question. Yeah, this raises the question is, can we still estimate the 3D structure even in situation where we cannot estimate the rotations? Because the biologists, they couldn't care less about rotations, okay? The only reason why I started with rotations is because as a mathematician, I was being taught, okay, how to solve a problem, just bring it to another problem that you already know how to solve. Okay, so I knew how to solve the medical imaging problem, okay, the linear inverse problem, that assumed that non-rotations. So, okay, let's try to estimate rotations, and then after I estimated rotations, problem solved, okay? But biologists, they cannot care less about rotations, okay? They want just a 3D structure. So the question, can we still solve for the 3D structure at any SNR, even in a situation where rotations cannot be estimated? So obviously the answer is yes, otherwise the talk would be over now. And you should know that the way that reconstruction works, whenever you see a 3D structure by cryo-EM, it was probably obtained using maximum likelihood estimation. And the way it works is actually very similar to what the oracle does, okay? Basically, it's called sometimes it's called iterative refinement, where you start by guessing a 3D structure, and then you're making projections out of that guess, and then matching the experimental images to the 2D templates. You get rotations, and now you can do a new 3D reconstruction because now you assign rotations, and you repeat this. The way I just described it is hard assignment. In reality, you do a soft assignment. So you don't commit yourself to a specific projection template or specific rotation, but rather you give weights, probabilities, basically in a probabilistic framework, a maximum likelihood framework. And this is the E step, and then the M step is just tomographic reconstruction, so it's the expectation optimization algorithm. And in this framework, you treat rotations really as latent variables, and you marginalize over them in the maximum likelihood framework. So really the parameter of interest here is the 3D structure, and everything else are just latent variables. So maximum likelihood is still consistent and so on. Bless you. But you still have some issues, okay? So we know that EM may not converge to the global solution. It can be very slow, especially if you're dealing with large data sets. And more severely, right now there is some threshold on molecular size. This is 40 kilodalton. It doesn't mean much to you, I know, but below, this is like the median size of protein in the human genome. But below this size, people were not able to get 3D structures in prior because the SNR is too bad. And so the question is some fundamental limit with the EM algorithm or something else? So we're going to take a slightly different approach, okay? And instead of using maximum likelihood, we're going to use method of moments, okay? So method of moments, I don't know, this is historically it even like preceded the maximum likelihood of, let's say, of Fisher in the early 20th century. So method of moment goes to Pearson, now we're in like late 19th century. And so why method of moments, okay? So it completely bypasses estimation of rotations. So we're just going to look at statistics of the images. And in terms of computation, it only requires just one pass over the data to compute those statistics. So unlike EM, where you have to do iterations until convergence and you go through the data every time, you were just going to do one pass over the data. Okay, so what are the moments? Okay, so very simple, just like average statistics. So the first moment is just taking all the images and averaging them. So the first moment has the size of an image. Second moment, very similar to what you do for computing the covariance, but you don't subtract the mean here. So just take two pixels, like x1, y1, x2, y2. You multiply their values, and you go again through all your images. And the same you can do third moment, fourth moment, fifth moment, and so on. And the question, can we estimate the 3D structure from those moment statistics? And if so, how many moments do I need? Okay. So first of all, let's realize that what's the size of the moments, okay? So let's say the first moment, as I explain it, is a 2D image, okay? But really it has a rotational invariance, okay? Because prime images can appear with all possible in-plane rotations. So it's very easy to convince yourself that also the average is going to have this invariance, meaning that it's only going to be a function of the radial direction, but not a function of the angle. So it reduces to just be 1D, not 2D. And the same, the second moment is only a function of the distance of the two pixels from the origin and the angle between them. Okay, so instead of being 4D, it's going to be 3D. And then you stop yourself for a second and say, I want to reconstruct a 3D structure, and the 2D moment is 3D. So maybe the first moment and second moment are sufficient to reconstruct the 3D structure. Maybe they have enough information, okay? The number of parameters that I need to reconstruct is like n cubed, the size of the molecule. I have n cubed information in the second moment. Maybe that's sufficient. That would be wonderful, right? All it means that I need to do like PCA of my images, and the information in the eigenimages and eigenvalues is sufficient to get the 3D structure. And we have all this machinery for PCA, even in high dimension. That would be fantastic. Okay, so let's see if there is enough information. So let's take us again to the late 70s, early 80s. So there is this paper by Zvi Kapp from the Weizmann Institute, exactly about that, okay? So reconstruction of structure from of randomly oriented particles. And what Kapp showed is actually you get a lot of information from PCA or from the second moment, But if the distribution of rotations over SO3 is uniform, okay, if it's the Haar measure over SO3 and the particles do not have any preferred orientation, then second moment is insufficient. And now I want to explain to you why this is the case, okay? Okay, so you already know the Fourier projection slice theorem I told you about. So what is the second moment? The second moment, now if we compute it in Fourier space instead of real space, the second moment, now it means that now I take two frequencies, okay, instead of two pixel values. Let's think of two frequencies in the image plane. And every image now will give me those two frequencies, but at different locations in the Fourier space. But they're all related by some rotation in SO3. So now when I average over them, it's like doing, say, Monte Carlo integration over SO3 of what? Of the Fourier transform of the molecule times itself. Well, the integral of the Fourier transform of the molecule times itself over SO3 has a name, okay? It's called the autocorrelation, or basically you just convolve the molecule with itself. And so we know that, for example, is it enough to recover the function from its autocorrelation? Well, we know that in 1D, this is insufficient, right? You take the Fourier transform and you get the power spectrum of your signal. So it tells you a lot about the magnitudes of the Fourier transform, but nothing about the phases. That's like the famous phase retrieval problem, okay? So now if we do the same over SO3, the language that we need to use for Fourier transform is that basically we need to expand our molecule in spherical harmonics, okay? So here is a spherical harmonic expansion with radial functions that are unknown, okay? And the information that we get, okay, I'm not showing you the derivation, but you can either look at the paper or do it yourself. So basically from the data, from the images, you can compute for every L in the spherical harmonic expansion, you can compute this basically matrix CL of K1, K2. So this is given, this is known from the data. And it's related to this expansion as follows, okay? So really, for every CL in matrix notation would be AL times AL complex conjugate transpose. So you can get the Cholesky, let's say if you do Cholesky decomposition of the CLs, you get the ALs, but only up to a unitary matrix. So you see, this is like the analog of the phase retrieval problem, where you don't know phases. Here you don't know unitary matrices. Okay, but you do get a lot of information, but you are missing those unitary matrices. Okay, so we see the second order moment is insufficient. Already come, okay, okay, let's use some slice of higher order moments. You didn't want to use all third order moments or fourth order moments because they are huge, okay? And you cannot deal with it, okay? And you notice, like, at least empirically, very low resolution uniqueness results. Much later, okay, so my former student, Professor Bandera, and his collaborators, they have a beautiful paper published in Nature a couple of years ago that shows that, yeah, like third order moment isn't this sufficient to guarantee uniqueness. More precisely, finite number of possible 3D structures. With my former colleague at Princeton, Emmanuel Lebel, that we talked about yesterday over dinner. We show that this is like information theoretic optimal. So basically, in the case of uniform distribution, no other assumptions, you cannot do any better than this. And this is actually a surprising result, like if you see it for the first time, because typically for statistical estimation problems, the sample complexity, the number of samples that you need, would scale as 1 over the SNR. Okay, so if you have a Gaussian with variance sigma squared, and now you want to estimate the mean, the number of samples that you need will scale as sigma squared, okay, to any given error that you want. But here, because of the latent variables, the missing rotations, you see that the number of variables that we need scales now cubically with the SNR, because we need to go to third moment. The third moment means that I'm multiplying 3 noisy pixel values, and so the lower SNR regime, this means that now the noise variance is amplified cubically because I'm multiplying 3 pixel values. So I need number of samples much higher. I need to scale a sigma to the 6. And that's, I don't know, it's a bit of bad news because computationally it's difficult to do computation with third moments, okay? It gives rise to very large, I don't know, moment tensors, and we don't know how to, there are no like nice tools that we have from high-dimensional statistics to deal with the covariance matrices and do eigenvalue shrinkage to improve estimation. And so, can we somehow avoid this third order moment? And the answer is that sometimes we can, okay? So the result for the third order moment that guarantees uniqueness is necessary in the case of uniform distribution, but actually in practice, molecules do have preferred orientations. And somewhat surprisingly, we show that in the case of non-uniform distribution, you don't need to know the distribution, just that it's non-uniform. Actually, second order moment is sufficient. Okay, so somehow it breaks the symmetry, the nice separation of spherical harmonics. Okay, and now all the spherical harmonics are interleaved and connected. And really you get a large system of second quadratic polynomial equation in the 3D structure, and linear are in the Allen distribution. And you can show that you can get, under certain conditions, you can get unique solutions. Unfortunately, this is just a paradigm right now, okay? We can only get reconstructions at very low resolution using this. But at least you get something, at least for ab initio. Another way to avoid 3D moments is using a sparsity assumption, okay? So if you have some prior on your molecule, for example, that you can represent it as a bag of atoms, okay, as a mixture of Gaussians. Or let's say in the weather domain that you have a really rapid decay of the coefficients. In those cases, the second order moment is again sufficient to reconstruct the molecule. You don't need to go to third order moment. Okay. Another case, so I mentioned the AlphaFold, the recent Nobel Prize. And you can use it to get an idea of how the molecule should look like. So if you know that like you have a very strong power on the molecular structure, now you want to combine it with your, with let's say just second order moment, you can do that, okay? So for example, you now want to find this the missing unitary orthogonal matrices that would make the structure as similar to what AlphaFold, let's say, gave you. And then you can still solve it with just second order moment. From the theoretical point of view, I want to mention those really interesting theoretical works, okay, that show, I would say, like a nice and like deep connection between maximum likelihood and method of moment in the limit of low SNR. Okay, so you can think of the SNR as a small parameter, okay, when you're dealing with very noisy data, and basically expand the likelihood function in the small parameter, in the SNR. And remarkably, what comes up in that expansion are the moments, okay? So the term that will multiply SNR will be first order moment. SNR squared will be second order moment, and so on, with some coefficients, okay? So it gives you like really nice connection between the likelihood function and method of moments, but not just for this problem of cryo-EM, but for other problems as well, like Gaussian mixture model. So this was done in this work of Bandera and Katsevich, and the orbit recovery problem, cryo-EM, and so on. So computationally, it gives you a hint of how to combine those moments when you try to do the optimization. Okay, so at the end of the day, I'm going to solve like the least squares problem. But now it tells me that perhaps what I should do is to give different weights to different moments, okay, where the weights I can take from this expansion of the likelihood function. And I'm going to give an asymptotically smaller weight to third order moment compared to the second moment. And so sometimes the way to do it isn't just, because the weights are so different, you want to do moment matching, just start with first moment, then second moment, like you're just on the manifold, satisfied by first moment, second moment, and so on. Or you can just do a weighted least squares. So this relates to what is called the generalized method of moments. perhaps some of you have heard. Again, this is associated with a different Nobel Prize, actually this time in economics, for the generalized method of moments. Okay, so now I want to go and talk about heterogeneity in the 10 minutes left. So this is just a slide from basically a paper in the journal Nature Method that selected this direction, what is called the dynamic direction for quarium, is one of the methods to watch recently in 2022. So basically, how to solve 3D structures that can actually that are not rigid. Okay, so for example, here you see just a cartoon of something that can open and close. Okay, so the sample of molecules will actually consist not just of a single 3D structure, but all of this range of motion. In this case, it's 1D motion, but motion can be with several degrees of freedom. You don't know it ahead of time. A much more difficult problem to solve than just like one 3D structure. Okay, so again, I'm not going to take you through all the history. There are very mature techniques for how to solve in the case of what is called discrete heterogeneity, when there is just a small number of what is called metastable states for the molecule. Okay, let's say just 2 states or 3 states or 5 states. Okay, and then you can extend the maximum likelihood framework to have another latent variable, which is the class. Okay, and basically everything extends nicely. But it is the continuous motion that is much more difficult. And again, you have like a flurry of methods being proposed in recent years. And nowadays, as you can imagine, there are lots of techniques that are based on deep neural nets. First, Dragon, that is developed by Ellen Jones with my colleague at Princeton, is perhaps maybe most popular right now. Nowadays, it's basically a version of a rational autoencoder. In my group, so together with my former postdoc Mark Jeeves, who is now assistant professor at Princeton, we developed a completely classical method. By classical, I mean it's just based on applied math and statistics, no deep neural nets, that we call recover or recovar. It's a shorten for regularized covariance. And I'm going to show you now that it actually outperforms all the other methods, including the deep neural net methods. And so that's maybe something, okay, we'll talk about this, that even though we are in like, I don't know, the modern era of AI and machine learning, and it's basically impossible to avoid, okay, anywhere you go. And I get this question all the time, like, did you try deep learning? Like, how does it compare with deep learning? Okay, and I'll show you, yeah, we actually didn't do the benchmarking, okay? It was like independent benchmarking, and yet the method that we developed works better, okay? So there's still some room for, I think, mathematics and developing methods that are, I don't know, you can get like really quick results using deep learning, and that's maybe one of the main advantages, that nowadays with the software, there is like amazing software that anyone can basically quickly build a deep learning method, but and it will give you quite far, like, but you can still sometimes do better, okay, if you give a long thought to your problem. Okay, so this is like the result of the independent evaluation, and you see that, so it's actually from the group of Aaron Jong. They published it in New York last year, and they compared several results, several methods. Many of them are based on deep neural net, and as common in this field, the bold means the best, highest resolution. And so you see that for 4 out of the 5 data sets, recovar is doing better than the other methods. Even for the one data set that it doesn't, with some tuning of parameters, you can get better results. Okay, and also in terms of the embedding, so remember that in this case of heterogeneity analysis, you have a molecule that is moving, and in this case, let's say this first example, the motion is just one-dimensional. So let's say something rotating, and so you expect to see that the embedding should be like a one-dimensional closed curve, okay? And you see this is exactly what we get here. And the other methods get some flattening of this curve. Maybe it even looks like two-dimensional, okay, or something, I don't know, other weird things, okay. So it also gives you a better notion of, okay, about the motion. So maybe now is maybe time to show the PowerPoint movie. Okay, so I'll switch now from okay. So just to give you again a sense of difference between continuous heterogeneity and discrete heterogeneity. So you see something is on the left hand side is moving, the discrete heterogeneity just of different classes, and here are the different methods. So the way continuous heterogeneity works, typically all methods have like 3 steps. The first step is to take the noisy images and embed them in some low-dimensional latent space. So this will be like the latent coordinate system, and also estimate density in that latent space. So for example, the hotspots here may correspond to, I don't know, metastable states, okay? And in the second step, for every point in this latent space, you'd like to get a 3D structure. Okay, so this will be the reconstruction step. And finally, you want to also estimate motion, okay? So let's say if I don't know, Helmut tells me, okay, I have those 2 metastable states, okay? Okay, this one and this one. Can you now show me what is the motion that will take me the structure from here to the structure here? Okay, and now you need to find some motion in this latent space, and I need to show him all the reconstructions along the way, so we can also do that, okay? And oftentimes it will not be just to take the shortest path, okay, just to take a cut here, because here's a region of very low density that probably the molecule doesn't want to go through there. Okay, so for example, in Ruediger that I mentioned of Ellen, the way the steps are done is basically you have a variational autoencoder, and so you have an encoder that will basically do the step 1 for you, okay? It will embed your images in a low-dimensional space, okay? And then you have a decoder that will take you to the 3D structure. And you train it by basically saying, okay, I want the projections of this to be close to that, okay? And that's how you optimize and find the ways. There are much more to the story. I'm not going into all the details of Ruediger, but just to give you an idea. One thing that's missing in Ruediger is there is no simple way than to look at the embedding and find what is the motion, okay? Because it completely distorts this non-linearity completely distorts the embedding, okay? So and the densities along this manifold of information. Okay, in Recover, okay, so this is the work with Mark. The steps that we do, as I mentioned, it's nothing that has nothing to do with deep neural nets. The first step is some variation of PCA, okay? And I need to explain to you how to go from, so really what we want to do in this problem is to go from the 3D structures and to do PCA of the 3D structure. But we only see the 2D images, we don't see the 3D structures. But we have a way to actually do this PCA only from the 2D images and basically get this embedding and density. Then the reconstruction is done using kernel regression, okay? And then we also have a way to find the motion, okay, by solving Eichelon equation in the embedded space. Again, PDE. But so it's all classical applied math. And I want to show you some comparison between the results. So here is like from an experimental data set. This is the embedding that you get using Ruediger. This is the embedding that you get using Recover. More or less the same if you ignore the coloring. Let's see just reconstruction of state A. Okay, so So basically, these are the two structures. You can see a lot of like noisy artifacts in CryoDragon, even like a missing piece. Okay, that you know the class. It should appear here. Okay, you see it here. Here is a different data set. Okay, so this is the reconstruction by recovery, by CryoDragon. Again, lots of like noisy artifacts. And if I'll do some zooming for you, okay. Okay, so for example, look at the red part here and the red part here. You can much more clearly see the helix here, and that you don't see it here. Or if you look at the zoom in here compared to the zoom in here, you can see much better resolution. And also, as a bonus, also the runtime, because it's basically we're doing just linear algebra operations for PCA and so on. The running time is faster. Okay, so on one GPU, our method is about 1 hour compared to 20 hours, and for other data sets, it's about like 10 to 20 times faster. Okay, so maybe just switch now back to the PDF and I'll summarize. Okay. So, yeah, so if I just need to tell you how it works, I'm not going to go through all the 3 steps of the algorithm. Maybe I'll just give you a hint of how the PCA of the 3D states from the 2D images work, because it has to do again with the Fourier size theorem. Okay, so basically, if we want to estimate the covariance of the 3D structures just from the 2D images, we'll just focus on 2 3D frequencies, and now you can look at all the images, the 2D images that go through those 2 3D frequencies, and estimate the correlation or covariance based on them. Okay, so this shows that even though you don't see the 3D structures directly, from just 2D projection images, you can estimate the 3D covariance. Okay, so we are in a sense lucky that we're in 3D and not in 2D. Okay, you cannot do this game in 2D tomography from just 1D projections. Okay, so many of the algorithms that I talked about today, you can find them in Aspire, the toolbox that we developed, open source in Python. It's meant for method developers and mathematicians, engineers, that really to save you from all the trouble of getting into this field. And to summarize, well, the first part was dedicated to show that really cryo-EM is transforming the field of structural biology. The second part, that cryo-EM reconstruction is a mathematically very rich problem. And I kind of joke with, I don't know, students, postdocs, others that want to think about cryo-EM and tell them, okay, just tell me what kind of math you're interested in, and probably I can find for you something in cryo-EM that you'd like to work on. Okay, because it really involves many different areas of mathematics, numerical analysis, information theory, statistics, optimization, even computational algebraic geometry, representation theory, dimension reduction. So, yeah. So with that, I'd like to thank you and all the funding agencies, of course. Thank you.
Thank you very much for a great talk. Yes, Philip?
When you talked about the small proteins,
you talked about small proteins and that they were a particular problem due to the low SNR. I guess they have like a few thousands of atoms or so in that range, or is this, or would, I mean, that's a range where something like DFT would probably also somehow be usable.
First of all, we're talking about tens of thousands. So 40 kilodalton mean maybe 40,000 carbon atoms.
Okay,
yeah.
and
it's a bit larger.
I mean, there are also some surrogate models which kind of are capable of interpolating, of efficiently computing potential energy surfaces. Would this help, or could this help as a kind of a regularizer that some
configurations could be ruled out because they have higher energy or something like that?
Right. So what you mentioned is very interesting. I mean, so people also think about it not for the reconstruction part, but also for heterogeneity analysis. So when you want to find the continuum motions, and they think about, okay, let's do like an MD simulation, okay, around some structure that you found, and see, okay, what kind of motions would be predicted by MD simulation, then combine it with the experimental data by cryo-EM. Okay, so there's like another possibility of how to get pyros from like the physics of the pole, the chemistry of the pole, like what you mentioned. Yeah.
Could you not embed this sample into something that has a known signal outside that is much clearer? Because it's just the alignment that you need, right? Put it, let's say, in a plastic before you thing, and this plastic has some kind of structure, right? Which is very clear, and you can actually, and you know that, right? I mean, it might even be something that you can build where you know what the structure is. And then you do first the angle matching on those things, right? Because it's just a matter of registration, right?
Yeah, so yeah, another excellent question. Actually, this is being done, okay? So it's sometimes much more difficult to do. So people build some nanodiscs that you can attach molecules to, or like even like artificial spherical membranes that the protein will attach to. Some people build what's called a scaffolding cage, or like cages that will even like the same protein will repeat itself a few times, and this will be large enough, or to bind it to something. So they try everything that just not plastic, but they try. Yeah. So whenever possible, they will do it. Okay. But still, there are many proteins that still they didn't figure a way of how to do it experimentally, and it's tough. Okay, like to do this compared to just freeze your sample, compared to now let's do this entire experimental design and try this something that's difference of years of research compared to something that you do over days in the lab. Okay, so of course an advantage of something like general that would just we'll just collect more data and we'll solve the problem.
There are probably more questions than we can take. Holger.
So I would be interested. So at some point, I guess you need to estimate the moments, or like basically covariances or higher moments. So if you want to get an idea how many samples you need, I guess you need error bounds for those. Mm-hmm. So, I mean, are you using known things, or maybe it's also, are there possibilities to exploit some pre-knowledge about the structure of the covariance matrix to get better bounds?
So, second moment, we have really good bounds for second moment, just covariance estimation. It's the third moment where things start becoming more fishy, but the most simple bound is just what I mentioned, okay, that the variance will go like sigma to the 6, you just need number of samples to be of that order, and then you can control the error. But this is very ad hoc, okay, because you know that high frequency, you have much fewer information, and so the bound will depend also on the frequencies, okay, and the pulse spectrum decay of your signal. So so if you can include this kind of power information, that would be useful, okay. And we know a little bit about proteins, okay. There is something called like Wilson statistics that tells you about the decay of the power spectrum even ahead of time, okay. So the bilaw at very low frequency, so we can also incorporate this information as well.
So for instance, if you have sparsity information, you can like get bounds which are much better than the generic ones, at least for the covariance matrix. Don't know about higher moments, but
right. But you don't know We can talk about this.
Yeah, let's talk offline.
You can do like sparse PCA if you present it like in the wavelets and so on. Right, you can leverage those ideas. I don't know about like the higher order moments, like 10 of and so on.
Okay, let's thank the speaker again for an amazing talk. And we have the last talk, which is also not according to the, or who is it given? Okay, yes, that's what I thought. We have a permutation of the speakers, but not across days, just within the day. So yeah, the last talk will be given by Wolfgang Dahmen on compositional sparsity.
So let me see. This is just what is the pointer? This thing?
Yes.
Okay.
Bring us forward, bring us backward, and then there's the laser.
Okay. I'm on. Do you hear me? Okay, so this is what I'm going to torture you with. This is now switching gears quite a bit from previous talks because it's essentially pure approximation theory. Your fault, Helmut. Anyway, so here's a brief outline. I first want to spend a couple of minutes on the background to explain my logic in this. I think it's important to follow the talk. So, high-dimensional approximation is my topic, and it has many sources, like machine learning in general tends to be dealing with high-dimensional function recovery. PDEs in high-dimensional phase space are important models where you try to propagate probability distributions. Uncertainty quantification, when you deal with parametric models and have to propagate uncertainties through these models. And finally, operator learning is intrinsically high-dimensional because now you are mapping fields, and fields depend generally on infinitely many parameters. So some of them will be activated during a particular computation, but that number even changes. And so this is, in some sense, infinite dimensional. So, and the difficulties aggravate along this line. Okay? So, in generally, when you try to approximate a function of many variables, say d variables, then you run into a problem that when you use conventional methods that are typically developed in a low-dimensional regime, then you have a bad scaling into complexity, namely that the work or the complexity or the information that's required to recover an object to epsilon accuracy scales in this way, where there's a constant alpha in front of the dimension, which is 1 over the smoothness in general. So, but even if you have high smoothness and alpha is fixed, then of course this is going to kill you. And even if you assume an excessive amount of smoothness, like your function has infinitely many derivatives, and all of them are bounded by 1. There was a famous result by Novak and Wozniakowski that says that the number of information, say functional evaluations, to recover such a function is exponential in the dimension. So this is somewhat daunting, and is usually referred to as the curse of dimensionality. So more or less what I'm going to talk about is around the curse of dimensionality. So it's perhaps worthwhile just briefly recalling how it typically shows. Like a conventional spline approximation, in low D, you get a projector with respect to piecewise polynomials with a certain mesh size h. And typically the error scales like h to the k when you know the function has k derivatives, so to speak. Okay. If you transform the mesh into the number of degrees of freedom coming with an h mesh size, it scales like this. And if this is your accuracy, then you see that the number of degrees of freedom required to get that epsilon scales like this. So the alpha on the previous slide is 1 over k. K is the smoothness. So what you learn from this is smoothness and regularity in the classical sense doesn't really help in high dimensions. It's almost meaningless. localization and mesh refinement, so there's holy grail in low dimensions, adaptive methods, and so on, doesn't help either. Localization doesn't really mean much in high dimensions. And here is something important to notice. And you may say, oh, everybody knows this, but I tell you, I've been sitting in many talks where this was apparently misperceived. So there is no method that defeats the curse of dimensionality per se. This is nonsense. So all you can say is, for a given model class, for a given model class, you may have a method, an approximation method, or a system of functions that can beat the curse of dimensionality for that particular model class. Nothing else. So it's always the two that are needed in order to make a meaningful statement. There are these recent talks about Kolmogorov nets, which insinuate that this is a kind of a general defying the curse of dimensionality, which is nonsense. I'm sorry to say it in this way. So it's the combination of the two that's interesting. That has to be kept in mind to follow the next arguments. So what about model classes? So there's a central theorem in approximation theory that went over many decades, and the overarching theme was to characterize approximability by regularity, by smoothness. Say Sobolev smoothness, Bessov smoothness. And this has actually influenced a lot of work in expressivity of neural networks as well. But there is a but. What does it mean to have certain regularity? Regularity is an intrinsic complexity measure for compact sets. And in my view, the best way to express it is in terms of entropy numbers, the metric entropy, which measures directly the thickness of a compact set. So maybe for those who don't recall it, what is En? En means this is the smallest radius you can take so that an epsilon cover of that, with that radius, using 2 to the n centers, is a covering of the compact set. So in other words, n is the number of bits you need to encode the centers of such a covering. So this measures the complexity, and for all smoothness balls, yes, so Sobolev, this is essentially known, and you get this wonderful scaling again, which I showed before. So why are these entropy numbers now important? They are important due to the following results, which is sometimes subsumed under what's called Karl's inequality. So Karl's inequality says, if you are looking for an approximation method that is stable and which uses n degrees of freedom, so, and this leads to notions of, say, n-width, nonlinear n-width, where you don't insist on approximating from a linear space, but maybe from a nonlinear manifold. And the dn is sort of the best error, the smallest error you can achieve by investing these n degrees of freedom. And if you insist on this, on the underlying encoding method, on decoding methods to be stable in a quantifiable sense, then Karl's inequality holds. In other words, if this goes like n to the minus alpha, then the entropy numbers must go like n to the minus alpha. You can weaken that stability to growing Lipschitz constants, then there may be some log terms on both sides. But this is the essence of it. In other words, the entropy numbers limit what you can achieve with a stable method. This was my question when you go to more and more complex systems and wonder about expressivity. It may be meaningless in a way, because there's an intrinsic limitation. Okay? Otherwise, you could recover by a one-dimensional manifold if you allow a space-filling curve. But this is so unstable that it will never be relevant in computational terms. So smoothness does not suffice to avoid the curse of dimensionality. This is all you know. So the question is really what are relevant model classes in high dimensions which allow you to say something, and what are the corresponding approximation systems that can do something for those model classes. That to me is an important question, and this is what I'm going to be addressing in this talk. So let's look at what are the typical systems, approximation systems. The first one, maybe highly explored, is n-term approximation for dictionaries. Here you have a collection of basis functions or even spanning systems, and you are free to choose the best ones for a given function. So the nonlinearity is in selecting some of the infinitely many basis functions. That's a mildly nonlinear approach. Okay. The second one is this more nonlinear, it's low rank approximation. Why is it more nonlinear? Now you actually have to also find those low rank factors, which are functions of a single variable, and this has been very successful in many scenarios. For instance, you can rigorously prove that with low-rank approximations, you can solve high-dimensional diffusion problems without suffering from the curse of dimensionality, rigorously, in a sense. So, but it's very much tied to this particular problem. It doesn't mean that any other PDE can be treated in the same way. And then there is this final level of nonlinearity, which is much more nonlinear, which is neural networks. I don't have to explain this here, but the point now is the high level of nonlinearity comes from compositions rather than superpositions. So this is the strongest level of superposition, and this is sort of the highest level of nonlinearity in this regime, because it's built on compositions. So compositions apparently play a big role. So what is special about DNNs, aside from causing a big hype, but there are other reasons. So as I said, it's compositions rather than superpositions. So they should give a key. And on the other hand, this wonderful flexibility and the known expressivity, which is stunning to some extent, it also ties your hands, because the only really manageable way in practice to find a good approximation in terms of DNS is using optimization. But now you end up with non-convex problems, and there is this large uncertainty of optimization success. So in other words, there are pitfalls and there are drawbacks. And to an old-fashioned person like me, this raises the question, do I have to put up with this? In particular, if the neural networks for many problems can't do better than other methods I know, which are very stable, and I know exactly how much work I have to do in order to achieve a certain goal. So that to me is always an important question. So is there something that offsets the drawbacks? For instance, that something could be superior approximation power. That for certain problems where I know my established, well-understood methods cannot do the job, they will fall into the curse of dimensionality. Maybe the networks avoid it. Well, what is known about approximation power? Well, the widest approach in terms of expressivity is emulation. In other words, you realize, you pick a good method that is known, whose performance you know, you realize that its building blocks can be represented by small neural networks, and then you go. This is very nice in the sense that, all these different classical methods, they can be, in principle, can be matched by one single approach. This is nice. But by definition, you lag somewhat behind, because you rely on the classical method to have a certain performance that you then recover. Okay? Well, then there is superconvergence. And you say, for instance, for Sobolev balls, I can double the rate when I use a neural network. But then I'm back to my stability issue, because there is this entropy numbers of Sobolev balls that have a certain decay, which is the classical rate, and the question is this possible double rate actually achievable in a stable way? So anyway, so the way you turn it, there's always a question mark. So in the underlying question to what I'm talking about here is, are there reasonable settings where deep neural networks can actually do better than than the classical methods, which rules out emulation as an approach. So there has to be another angle to be pursued. So that's the overarching thing. And this is what brings me to this kind of sparsity notion, which is directly building on the main structural feature behind your networks, maybe on compositions. So what is about this? So, okay. So our building blocks now, and this is important, and to me at this point, are continuous functions, not finitely parameterized functions, not functions that depend on a given number of degrees of freedom, just a bunch of continuous functions. Let's call them G. These are these mappings. They may map from a Euclidean space into another Euclidean space. The point is, they are supposed to be compositions. So they have, say, n composition factors, which is a representation of the same mapping, because there are, of course, is a universe of different compositions. You can put in identities in terms of mapping, so it is highly non-unique, but the bold-face G will be one such representation that gives the mapping G. So that's the notation. So what's the goal? My goal is to describe a regularity of a function, its structural sparsity, by closeness to nice compositions. So, if given a function, can I find the composition of mappings with certain properties nice, which is actually close? And if I have certain parameters to then start to enlarge, can I get closer in a quantifiable way? And this will be the regularity of the function. Like in low dimensions, approximability is equivalent to regularity. So the intrinsic property of best of smoothness can be equivalently expressed by approximability from certain objects. Okay? So that's a very similar line of thought. So the question is, what's going to be nice? What's nice about what has to be nice? And again, this Kolmogorov superposition theorem may give a hint to that. Namely, it has a very strong statement. It says every continuous function, if I translate it into this language, can be written as a composition of depth 4. And each composition factor is either trivial by being an affine function, which I don't have to approximate anymore, or it depends on a single variable. So when I be talking about S sparsity here, S is in this case even 1. So nice means I can say something about these composition factors, namely that the components in these factors depend on a smaller number of variables than the total number of variables. Say the whole function may depend on D, like 1,000 variables, but these composition factors, each component in it may depend on a much smaller number. And in the Kolmogorov theorem, this is 1. So what's the wrinkle in the Kolmogorov theorem? The wrinkle is that there is at least one function in this composition where you cannot quantify its smoothness. It's just continuous. And it could be arbitrarily hard to approximate. So there's no gain. So in other words, you have to impose an additional thing on the composition factors in terms of stability. But as soon as you do that, you of course have to stop requiring that there's a finite depth. Okay. So that's the rationale behind those. In other words, I have a structural condition on composition factors, that is, those guys, the components, are allowed to depend only on a few number of variables, S. And the second is they have to exhibit some stability. So that stability I have to quantify. And I need what you might call a regularizer. It's something that quantifies your particular representation G and maps G into a number in R+, which says that's so stable. Okay. So I will make that precise in a moment. In addition, I have to give it a certain complexity. Although this is functions, these are just continuous functions. There's not a finite number of variables determining these functions, but still you can take this complexity measure, which simply counts in each of those composition factors the number of active variables. This is S. S of the J's composition factor and the I's component just says, oh, this guy depends on at most S variables. The original D may be much larger, but I allow only those. And then the complexity of this particular representation I would call N of G, which is simply the sum of those active variables. And if these were neural networks, you would have this kind of classical complexity bound. And then finally you have your competitor class, namely the class of compositions which have complexity at most n and dimension sparsity s. This is the collection of all such mappings which have a representation G, which is dimension sparse and has complexity at most n. Okay, these are still continuous objects. They are not described by a finite number of variables, but they, to me, describe regularity of a function in the following way. So I put these things together and define what nice is. So this triple norm, it's not really a norm, but close to it, is simply assigning to a mapping G. This number, R of G, is a regularizer. And I take among all these regularizers the best one, for which the dimension sparsity is at most S, and where the complexity of this composition is at most n. This is this. So what could such a regularizer be? It depends on your application. You can vary it. For my application I will exemplify later, I will choose this one. Like the regularizer looks at the Lipschitz norms of the composition factors, and even of some subcompositions of it. But this is a fixed number, and for every G I give you, I have to determine this sort of best composition choice, best representation, which defines this norm. And then I do something very classical in approximations here. I look at what's called, maybe what you could call a K function. In other words, I give you no generic function V. I don't know anything about V. I want to describe its regularity in terms of compositional approximability. And how do I define it? I say, how close is V to a nice tamed composition? So I look at guys from this class, which have these finite composition norms, and look how close can I get to them, but also I want to keep their stability norm small. In other words, I add it as a penalty, and that compromise I'm allowed to depends now on delta, which is a parameter in this K functional. So this formally looks like a K functional, which is used in approximation theory all over the place. All right? So how do I define now closeness in a general way? Well, I have to relate delta to n. Okay? Because n is the complexity. So how do I do that? I look at it, what I call a growth function. Something is strictly increasing, going to infinity. So gamma of r could be r to the alpha, or could be e to the r. And I will make these two examples all the time. And then I say, I look for a V, and I put as a penalty gamma n to the minus 1. So something that gets smaller and smaller when n grows. And I ask, if I now multiply this K functional by gamma to the n, stays this finite? And if this stays finite, this is the semi-norm that quantifies approximability. So in other words, I ask whether for a function V has a K functional, which for these deltas decays like gamma to the minus n. Again, this is a special case for my application. Later I can tune this and modify this to have much more varied classes, but I think for the technical reasons is enough to, and it shows the essence. And now you have an approximation class. Namely, you look at all V in a Banach space, say L infinity or C, for which this norm is finite. In other words, which have a k function that decays at this rate. So this is normal approximation class. You can show that this is a compact subset of X and things like this. So this is a model class. And you can guess that this model class is relevant for approximating by things like neural networks and everything that relates to compositions. So, but to simplify the thinking, when you see a function v is in this model class, it immediately comes from the definition that it really means there exists a G in this composition class. These are finite compositions, which are nice in my sense defined before, so that the error, the deviation from those decays like gamma of n to the minus 1. So if gamma of n is exponential, then you would have an exponential convergence by good compositions. So this V would be exponentially close to compositions if you allow the compositions to have larger complexity described before. Okay? And it also means that the composition norms are all uniformly bounded by this new approximation class norm. It's very similar to nonlinear approximation in approximation theory. Very similar. It's not exactly the same because the degree of nonlinearity is much higher here, but there are a lot of similarities. And once you have that, there's a simple result. Actually, I'm always hesitant to call this a theorem, but I call it a theorem here because it gives you a strategy in the following sense. Namely, it means, so far my approximations by compositions were continuous objects, not determined by finitely many parameters. Now I ask for an approximation which I determine by finitely many parameters, like a neural network. And its immediate consequence, namely it says, if my function belongs to such an approximation class, then for every epsilon, there's a neural network being close to that function with an epsilon distance, and the number of trainable weights in that neural network is bounded by this. So I quantify the complexity of the neural networks in the classical sense. What is the number of trainable weights? So now this looks horrible. Let's look at these three factors. They are not that horrible. The last factor, forget about it. It's a log. So the log is not that much. The first factor is actually epsilon to the minus s. S is the active dimensionality in the factors. The whole function may depend on d much larger than s, but it's the s sparsity in the factor representations that surfaces here. This would be the accuracy for Lipschitz one function in s variables. Okay? And then there is this middle factor, but you see this middle factor depends now on that growth function, which determines the closeness in the k function. So if gamma is exponential, then its inverse is logarithmic. So you have another log. So essentially you get here your approximability in terms of Lipschitz smoothness. This is not much better you can do. If, however, gamma is just polynomial, it's an algebraic growth, you can quantify it as well, and you get something like that. So if gamma is like r to the alpha, you get a precise rate like this, and you can see if you let a alpha tend to infinity, sort of approximating the exponential regime, this recovers the old result. It gives essentially the estimate from before. You can actually also estimate the stability norms of those neural networks, but it's too complicated. I skip this. So, what does that theorem say? Now, if you want to assess the approximation power of neural networks, your homework consists of two parts. Part number one is you have to understand the compositional approximability of your object. And that's an approximability independent of architectures or anything like this. It's just of compositions that I call tame in terms of these nice properties. Then the final step is what I would call implanting DNNs. And this is based on known results. Like, in particular, Gita and Philip Peterson, they had these results. They say we can approximate, say, Sobolev functions by neural networks by controlling also higher order Sobolev nodes. I had to tweak it a little bit because I'm just for my application assuming Lipschitz, and I want to also control the Lipschitz norm. Not that they go to the difference goes to zero, but they should be controlled. And this is what it is. And the nice thing about compositions is, if you now look at a continuous composition and you look at these components that depend only on S variables, you just approximate each component by a neural network that has these nice properties. You still have a composition. And in fact, doing that for all non-trivial components, you get a composition of mappings that give neural networks, which is a neural network. So basically these two things. You have to understand the compositional sparsity of an object, and then you implant deep neural networks. So this is the rationale. So now this is all nice. It's almost a tautology. It's not that deep. It's just a handwork. I want to see whether this is actually plays out in a context of interest. The context of interest for me, I've worked on different classes of PDEs, and to me there are two extremes. On one end is the elliptic problem, which benefits from diffusion, mainly. It's a dissipative model. It forgives you a lot of things, and it gives you stability in terms of diffusion. And then the other extreme is just pure transfer. It transfers coverings into coverings, but it doesn't gain you anything. There's no dissipation. So I want to, and accordingly, model reduction for those models in high dimensions, they are not really, don't really exist. At least I don't know whether there's something. If I use this kind of model reduction, I defy the curse of dimensionality, because the mapping from parameter to solution is not at all smooth. This is not holomorphic like in the elliptic regime. So that's my interest. So what are the problems of interest? So that will appeal to operator learners. So I have a class of model of problem data and a class of PDEs that depends on these input data. Think of these data as initial conditions, source terms, convection fields, diffusion fields, whatever. Each instance gives you a specific PDE, and U will be the solution for that instance. Therefore, U becomes a function of delta of this data collection. So the solution operator takes the data that specifies now your particular PDE and takes it into the solution. And of course, it is of interest to learn this mapping, because if you have that mapping, and if you have quantification of accuracy for that mapping, you can use it for inverse problems and all sorts of things. It gives you a fast exploration of the solution manifold, which is the collection of all states that can be obtained by looking for the solution for that given input data. So it's just a range of your solution map acting on the data class. Okay, so that's my object of interest. So the complexity of this manifold is the same as the approximability of the solution operator. And remember, if D, the data class, is actually even infinite dimensional, is a field of functions, then you have essentially a problem with infinitely many variables. And best understood is, for instance, the case when this data class is a diffusion field in an elliptic problem. Very well understood, because the mapping from the parameters to the solution is in many cases under mild assumptions on the structure of that field is holomorphic. So, and one result is that linear reduced models do very well, because holomorphic functions can be approximated well by linear spaces. quickly decaying n-bits. So least understood, or much less understood, are transport problems or dispersive models, where no such counterpart is available. So this is what I'm targeting. So here's my model problem to see whether these concepts do give anything. Okay. So this is a simple transport equation. There's a convection term. There's maybe a reaction term right inside, and I will pose some initial conditions, blah, blah, blah. Same thing. But I would like to consider two such regimes. Regime number one is actually the differential domain is low dimensional, like 1, 2, or 3. It's transporting 1, 2, or 3 dimensions. That is, the spatial dimension dx is small. But the convection field is parameter dependent. And that may depend on a large number of variables. So you have a big variety of convection. So high dimensionality comes here from the parameter dependence of data, and that will include later the initial conditions, or the right-hand side, or the reaction term. So they are allowed to depend on design parameters, which come from maybe probabilistic models of parameters in a probabilistic model of transport. Okay. So the second regime is when I forget about parameter dependence, and I could add it, but it would be a repetition of that first one, and I assume that the differential variables are large. In other words, my transport equation is posed in high dimensions. So now you can think of A, the convection field, to be a fixed field, but the initial condition on the right-hand side and the reaction conditions, they may vary over some complex class. Actually, the A itself as well, but I'm suppressing direct parameter dependence. Okay, so if you only assume smoothness now on your input data, like initial conditions and right-hand sides or convection field, you are dead. Then you will not avoid the curse of dimensionality. This in this case is the nature of the transport problem. If you look at a parabolic PDE, it is totally different. So this is a matter of this problem, transport problem. All you can expect is a regularity theorem. Namely, if your data exhibits some sparsity, does the solution exhibit a similar sparsity, and can you quantify this? This is exactly the counterpart as in low dimensions when you say for 2 or 3D PDE, you say, oh, all the data are smooth, then my solution is smooth. And now the smoothness or regularity is classical, Sobolev, best of smoothness. But now I change gears. I say, if my data are regular in terms of compositional sparsity or some structural sparsity, can I show that the solution inherits this? That's all you can expect, because it's easy to show that otherwise you run into the curse of dimensionality. So this is what this is about. And there are now the two regimes. Let me state the main findings. So let's look first at parameter dependence. So the parameter dimension could be large, but the spatial dimension is just small, 1, 2, 3, and that's my sparsity, my dimension sparsity in this case. That's going to be the number S that comes into play. Okay. And let's be even more, one can be much more general, but for the sake of illustration, let's assume your convection field has a typical, is maybe the result of a probabilistic framework, and you have a Karaman law of expansion, where you have a superposition of functions that just depend on x and t, but their weights are the uncertainties. But these are the parameters. Okay? So your convection field in this special case is just all fields of this type, where dy could be large. So what one can then show is, using these things, these convection fields do satisfy compositional sparsity. In fact, in this particular case, and this is just for illustration, the convection field will belong to a Bochner space. It continues in time, but in space it belongs to a compositional approximation class where gamma is any exponential. So these guys, by the structure, they can be very rapidly approximated by finite compositions with a prescribed niceness and being dimension sparse of the spatial dimension. Okay, this is what you can show. So, but the solution manifold is tricky. It is not smooth. This is just a cartoon saying there are edges in there. So this has to be accounted for. It's not that smoothness that helps you. It's the overall structure that is going to be useful. And here is a somewhat simplified theorem. It says, suppose now your data class belongs to such an approximation class. Actually, it should be a Bochner space. So continues in time and then in space belongs to this. And this now refers to initial conditions, source theorems, and so on. Then, depending on parameters. And then, for each such datum, you can find a neural network that is close epsilon. And this is the complexity bar. In other words, the number of weights in that neural network stays at most like this. So how does the big parameter dimension enter? Well, you see, it enters here, only linearly. It doesn't enter in the exponent of the accuracy. The exponent of the accuracy, omega, is this number here. And this number is determined by the spatial dimension, +1. And then if you have very low approximability alpha, in other words, if your gamma of R is alpha, your alpha is very small, that means your closeness to compositions is very bad, then you are also hit here. But as soon as alpha is larger than the spatial dimension +1, then it's just this. And you get the same number as when you use exponential. So if you have very good closeness to compositions, namely the growth function being even exponential, so the k function will decay exponentially, then this is what you get. And the b is simply an exponent in a log term. So this is for parametric. So for large spatial dimension, you get a very similar result. Again, the data are supposed to be in such an approximation class, and then you get an approximation result is very similar. And again, the big dimension d, which is now dx is now big, and s is now an assumption that you impose on your data. They do have a compositional sparsity that's smaller than d. It doesn't mean the function depends only on S function. It's very hidden in a compositional approximation. You get essentially the same type of result. So maybe let me give you just a summary and then maybe an idea of what goes into the proof. It's not very much. I'm going to tell you there. So the type of results is what you get. Composition sparse data give you composition sparse solutions. And you can quantify it. The composition sparsity of the data in terms of the growth function, then you can find the growth function for the approximation. It says something about the manifold width. It says you can now exhibit, what we have constructed is an encoder and a decoder, and you have an upper bound for what is called the manifold width. Meaning that you say, how can I encode the data with n degrees of freedom and then decode it again so that this pair gets close to the real solution operator. And basically what this is it constructs a direct approximation to it. So it translates into an estimate of the complexity of the solution manifold and of course the approximability of the solution operator. So Yeah, in this case, the solution operators can be approximated without suffering from the curse of dimensionality if your data are composition sparse. And elements of the proof is very simple. As I said, but the homework is this general theorem. It says, do you understand the composition sparsity of your objects? Once you understand the composition sparsity of your objects, you implant neural networks, and then you have a concrete approximation. So all I need to show you is why these objects are composition sparse. Well, obviously, my class of functions is determined by characteristics. So if you have a transport equation like that, the convection field induces gives an ODE that gives the characteristics. Characteristics that tell you how information is transported in this context. And once you have the characteristics, of course, then you have a solution representation. And what it takes a solution representation is, well, you take another composition. And then you have to deal with the integration, which is increasing width, technically. So that's not... And of course, if you prescribe the Cartesian coordinates, then of course you have to go backwards, but it doesn't change the complexity. Now, so the question is, why are the characteristics composition sparse? And the characteristics are composition sparse for two reasons, at least. Number one, it's a semi-group property. That is, you can compose time segments. It's like a composition. So that's a natural decomposition. But there is another one, even more important for these results. If I just use this one, I would be discretizing an ODE, the neural ODE, and I would not get these results. I combine it with another one, namely the fact that characteristics solve a fixed point equation. Characteristics are fixed points with a operator, with an operator shown here. And this is a contractive operator. So this is what you do. You combine the composition, the semi-group property with the fact that fixed point iterations will rapidly contract into the solution of the characteristics, and that gives you kind of a framework for exhibiting nice compositional approximations that are also stable and that are composition sparse. And that's essentially this, and then you can give, I won't dwell on this, you can specify the composition sparsity of the characteristics. So the main statement here is, if the convection field belongs to this class, then the characteristics belong to a class like this. So you exhibit the compositional approximability of the characteristics, and then you do my implanting of DNNs, and then you get a DNN approximation of the characteristics, and then you keep composing. Okay, so that's now simply following the path. And this is it. I should say a lot of it carries over to other situations, like Hamilton-Jacobian, the classical regime. Unfortunately, you never know how large the classical regime is. It would be interesting to see how it carries over in the regime where you only have a weak solution. So when you have a weak solution, you have closeness to a parabolic problem. And now you have to sort of balance these two terms. And that's the same problem like with high-dimensional Fokker-Planck equations. If you say you have dominating transport, but there is a dissipative effect. So this is under discussion. Nonlinear conservation laws is another thing. They allow what's called a kinetic formulation. Namely, this is a lifted formulation in terms of a linear transport equation, where, however, on the right-hand side is just a measure. However, there are fixed point approximations to these guys, where in each iteration you actually execute a transport operator. So this is in principle amenable to this. In general, whenever you have a solution procedure which is iterative, like a fixed point iteration or another Newton iteration, you have a sort of a path to a compositional approximation. This is why I think this is important for solution manifolds in general. And that's it. Thank you. Sorry for going a little bit.
Thank you very much for a really, really interesting talk. I have many questions, but I think we have time probably just for one or two quick ones.
Thank you very much. First, to state the obvious, of course, I find this very, very beautiful and really like it. Thank you. So you started by saying that, yes, with neural networks, you can do everything that you can do with dictionary approximation, right? There's transference principle and so on. It's one structure, it's uniform and so on. How about going the other direction? Meaning, I give an object that is compositionally sparse. Can you prove that there is no superpositional, no dictionary that will actually avoid the curse of dimensionality?
No, not necessarily. There may be a simultaneous sparsity also in terms of
Exactly, right.
say holomorphic.
So, right, so there are two sparsity notions that actually play together, right?
And they could hold at the same time.
Yes, interesting.
But there are objects in this world where only one of them holds.
Yeah, so in those objects where only one of them holds, can you prove that there exists no dictionary that would...
That's a good question. I haven't done this in terms of I haven't done this, but I think yes, this is doable.
I think because then that would establish the neural networks reign supreme. Yeah.
Yeah, for the transport manifold, let's just say I don't know of any.
Yeah.
I don't know of any method that does it because all of this they suffer from because of the nationality in this case. So at least the minimum reduce model won't.
Yes.
And that you can say, but the other models based on localization, like wavelet expansion, won't work either. Shearlet expansion won't work either. They have anisotropy, but they still scale in space, and that suffers from the curves.
Good, great. Thank you very much.
Last question.
Also, thanks for this very nice talk. I have a question. I mean, basically, the proof is. I mean, it's also emulating like a time marching scheme or so on, and then computational realization. But I mean, the method of character. Okay, it's like the continuous. It composes the. Yeah.
The only way I use the semi-group property is to get the time segment for which my integral operator has a specific contraction like a half. So if I make epsilon, the target epsilon smaller, that composition will remain the same. And the accuracy is only gained through the fixed point operation. So I'm not emulating time marching.
I see. Okay.
The composition in the time domain is only to massage my contraction operator. Because that gives me epsilon to the power. This is more effective. I'm not emulating an ODE.
Okay, that's good. Thanks for the clarification. But for computational purposes, I mean, one could then discretize this a small time marching step and construct a numerical solver. For the computational realization, do you have ideas how one could do maybe even better with neural networks?
I would say, I'm not saying anything about the computational realization. This is an approximation theory. This is just saying, if I have to deal with a transport equation, it's at least worth using these neural networks. And in fact, the proof shows they have to be deep. So shallow neural networks will not work. Okay? So they have to be deep. But it's at least worth it. It's not a guarantee that your particular optimizer will find these. However, you could look at the proof and give the skeleton of the meta architecture for the neural network. And this will include the segments that use the semi-group property only. But they remain fixed. And in between, there are expanding networks being composed with each other. I could imagine an edit like this. I could imagine that prescribing this kind of architecture, the optimizer may have a much easier time to give you some. That's an interesting question.
Okay, thank you.
Great. I think we should probably conclude our morning session. So we had 4 really great talks. So let's give another round of applause. So there's lunch, I guess, in the same location as yesterday, and at least this morning the weather was nice, so hopefully it's still nice outside.